let's see, can we open the presentation? Ah.
Which one?
Yes. Okay, thank you. Okay, is it working? Can I start? Okay, then thank you. Good morning, everyone. Thank you for coming back, and I hope you had a good last evening and a good night's sleep, and are ready to hear a little bit about more and discuss a little bit more about chemistry. And so today we will moving and doing more chemistry and more synthesis, and tomorrow then it will be all day photocatalysis. And so as we move along, today I would like to show you a little bit. We talked yesterday about chemistry of furans and where the furans are coming from. Let me tell you a little bit what type of chemistry can be done with this, and I use this and as an advertisement for my group. I will show you a little bit of the chemistry we have been developing in our group. So before we start, let me see if I can switch this. Let me see if you're still all with me. So there's a new number, and I could tell you something about or I can ask you something about my country. So maybe you can tell me what the capital of Germany is. Okay, so the system is working. Okay, you are all very well informed. So Berlin is the capital now. Before the wall came down, before the reunification of Germany, it was Bonn, but then that changed in the 90s. The reunification took place in 1989, and then they decided in Germany to do to switch this to Berlin. So I show you a map. And let me see if I can get the pointer to give you a little idea where I'm coming from. So here's Berlin. This is our capital, has about 3 million people. Very often, if you come to Germany, you might fly into Frankfurt. So Frankfurt is southwest. And the other airport you sometimes fly into is Munich. So Munich is also a big city with 1.5 million people. And then just about an hour north, there is Regensburg. And I told you already, the university was built in the 70s, has a pretty new campus, but the city center itself is very old. It's World UNESCO Heritage Site. And so this is where I'm from, River Danube, very nice city. Let me ask you something. Again, if you compare now Regensburg with your capital, New Delhi, what do you think, how much bigger in terms of population is Delhi? Is it 10 times, 50 times, 100 times, 200 times bigger? Okay, I can see I have a few mixed answers here. I gave this question to you for a reason. And that is also related to chemistry. And that is that you need to take in information very, very carefully. And when you get information, sometimes maybe in the main paper, people make an introduction and they're referring to other work. Sometimes these statements which might be made referring to other words might not be entirely accurate. Sometimes because maybe the authors also have not read the paper so well. Sometimes because they want to make their study look in a better light. Also very often in the normal paper, not all the informations are given. So always very carefully check the supporting information. Sometimes you might find discrepancies between the main paper and the supporting information, or the supporting information might have details which are really vital to understand and also to reproduce maybe a paper. And you see what I did here is I tricked you. I gave you incomplete information combined with the fact that the map I showed you is not a map which was taken by some German geographic institute. It was taken by the Regensburg tourist office. And so two things happened here. I tricked you in a way that, let me go back, that I told you that our capital, Berlin, has 3 million people. I told you that Munich has 1.3 million people. And then I showed you Regensburg. And of course you did probably the right conclusion. You looked and said, oh, look at this. Munich is smaller. Regensburg looks almost as big or maybe as big as Berlin. And then you probably know that New Delhi has about 30 million people. And then one good estimation is that maybe Regensburg is 10 times smaller, or Delhi is 10 times bigger than Regensburg. The correct answer is it's 200 times bigger. And you see, this all came because I gave you incomplete, I never said how big Regensburg is, but I gave you information around this, which was misleading in combination that this map was taken by the Regensburg tourist office, and they wanted to make sure that everybody can find Regensburg on the map. And so they oversized this here. You see, this is something you find very often in papers as well. People say, we have an exceptional broad scope. Our reaction conditions are milder. Often not accurate statements. What does it really mean, milder? Some people say, oh, it's milder because I can do it at room temperature. But then you do a photocatalysis, you have to use light. So is light at room temperature milder than 60 degrees, but you don't need light, right? You really need to be careful, especially when it comes to judgment. And that is also what I say when we try to write papers, we try to make as little judgments as possible, right? Sometimes you say it's good yields. Some people might think it's a good yield is 80%. Some people think about a good yield of 50%, right? That's all judgmental, and you need, we all have to do this sometimes. We cannot always give the accurate numbers all the way through the paper, but you need to analyze information very, very carefully and look at different sources and recheck this, and in order not to draw wrong conclusions, right? And as I say, very deliberately, I tricked you here. And very deliberately also for the informations, I gave this 10 times bigger because I have drawn you to the 3 million which our capital Berlin has, and I thought you are going to make the same comparison. Okay, so much as a starter. I will do a small advertisement today. Combined, I show you a lot of chemistry which was developed by my group. And here you see a group picture of the current group. They were just about to go to one of our festivals. So you see especially some of our girls having the traditional clothes on, which we wear in Bavaria, and especially when we go to these summer festivals. Some of you might have met Victor. Victor stayed here for months in Indore for a research stay. So again, thank you for making him feel welcome here. And then you can also see a number of students, PhD students from India. This is Sunaina. I will tell you probably during the photocatalysis lectures a little bit what she is doing. Pavitra, Mangesh is hiding here. Tirtha is a postdoc with an EU fellowship, but he's about to leave now. His stay is over. So I think I don't think I have missed anyone. So these are my co-workers from India in the moment. And as I said, I'm very, very happy. It's great, great people, and I really like to work with them. So I would like to tell you what we like to do with furans and pyrols. And another tagline I like to use for this is turning hay to gold, because this is really where the furans and pyrols, I haven't really talked about this, but you can convert a furan very easily into a pyrol. This is really where they come from. And this turning hay to gold actually goes back to a publication which was published in 1865. Wow, that's a long time ago. And that was published by Jakob and Wilhelm Grimm. These names don't say anything to you, but they are very, very well known in Germany. And so the Grimm brothers, they published a paper where they said that this little guy here can turn hay into gold. And so that is the father of this girl here bragged to the king and said, you know, my daughter can spin hay into gold. And the king says, hey, that's pretty cool. So let's put her in a barn with a lot of hay. And then, of course, she couldn't do it. But then in the night, this little guy came. His name is Rumpelstilzchen. And he could do this. He could turn hay into gold. And so this way he could save the miller's daughter here. But then he also said, I want your firstborn son. And so all the story evolves. So it was a lot more than turning hay into gold. Of course, this is an interesting effect. That is a story which our government, before we had the euro, thought that is such a great story that they put the Brothers Grimm on our 1,000 D-Mark note, on a 1,000 D-Mark bill. This is like today, this would be making the cover of a journal, right? Here it was the cover on our money, on the biggest bill we have. 1,000 D-Mark was the biggest one which we would have. It's about 50,000 rupees. And then also Hollywood thought that is pretty cool. And so they made a movie out of this, about the Brothers Grimm and their publications. And so there was famous actors there. Matt Damon was in there, Anne Hathaway, and quite a number of people who were starring in this. So the publications of the Brothers Grimm, and of course you know it's not publications, it was all fairy tales, right? But these are very, very famous in Germany, and we as kids, we all read it. But let's think about this. And you are a chemist. Would you like to turn hay into gold? Right? I would ask you this, right? Is that something, and you don't need to answer if you don't want to. It's a hypothetical question, right? Would you like to turn hay into gold? We all like gold, especially for jewelry. That's what we used it for thousands of years. We use it for coins. More recently, of course, the big applications for gold are in microchips, right? There's, of course, it's a big thing. But if you think about this, would it really solve the problems of the world if we have unlimited sources of gold? We probably could make unlimited number of computer chips, but we would still not feed the world, right? We would still not having essential resources we need. And so, again, this is an answer. There's no right or wrong. You are right. In the current world, you would be rich, absolutely. But I would argue that what we are doing as chemists to make useful products which really benefit mankind are much more valuable. And we talked about this yesterday, right? Health, energy, food, right? This is all important for us. And so I think, again, you should be proud of yourself that you choose chemistry as a profession, because I believe that chemistry is really the solution to a lot of problems we have to solve in the future generation, your generation, to advance and keep the world a good and maybe hopefully even a better place than it is today. Okay, so very hypothetical. I'm going to tell you a little bit what we do with these furanes and pyrols, right? And you can see here, again, this is something we talked yesterday, and we'll show you very briefly again in a moment. The hemicellulose can be degraded to pentoses, and then by acid catalysis, it falls into this wall of aromatic furanes, right? And that is the driving force, the aromaticity here. And then you can convert the furanes by, again, catalytic methodology into, by reduction into this alcohol, by oxidation into the acid. And if you treat this with ammonia, you can also change the furane into a pyrrole. And so that is something we believe is useful because it is produced in parallel. It's produced from agricultural waste. Still has problems in the way how we can produce it. The acid extraction, talked also about this yesterday briefly, it is a problem. It's mainly produced in China, and if you ask for a quote, we did this. We wanted to buy a ton of this alcohol, and we got a quote from China, and it was 1,500 euros, shipping and the barrel included. I thought that is great. I thought I'd do this because when you buy it from Aldrich, it's 30 euros per kilogram. It's still not a lot, but you can see already everything you buy from Aldrich, usually if you want to make an estimate how expensive really the production cost is, you have to divide at least by a factor of 10. So I thought that's pretty cool. I wanted to order this. My university would not let me. They said, you will never use, before you get retired, you will never use 1 ton of this compound. Right? I thought it's cool because I wanted to do some of the chemistry on big scale, but they said buy it from Aldrich, buy a few kilos, that's also okay. So I will show you that you can convert these furanes in quite a number of different types of building blocks. We already showed you briefly the cyclopentanols. I will show you what you can do with this. We'll also show you that you can do cyclopropionation chemistry, catalytic and asymmetric, and that is a very useful compound. I can show you also, will show you that you can rebuild these furanes and pyrroles to 6-membered rings or even to 7-membered rings. And I will show you that you can make peroxides photochemically by inserting oxygen into the carbon-carbon bond. So I think quite a number of hopefully interesting chemistry where we can discuss catalysis with this. And so this is what I would like to do. And I show you also a few natural product syntheses, because that is also what we are doing. And you see everything which is in red and blue here ultimately comes from the furane. And so we are building together, and you see in some cases, this is a natural product we made. Essentially all the whole framework is essentially coming from these furane building blocks. So, and the modern spinning wheels we like to use for this is catalysis. I also briefly showed you that we do immobilized catalysts on magnetic nanoparticles so that we have magnetic versions of a lot of our catalysts. And we use photocatalysis, and in order to scale up, we also use flow chemistry because this allows you to run reactions in a continuous setup and scale them up by just letting the reaction run longer. So it's a very convenient way to do this, and we will also talk about this a little bit more. I would like to go back of the two reactions we already have seen. I showed you yesterday that these furane alcohol, you can convert in this livolinic acid, and you can, if you have later on time and interest, you can look again through the mechanism. It's essentially all protonation, reprotonation chemistry, and water elimination. But the interesting thing is it's pH dependent. If you use a strong acid, you will end up with a livolenic acid, which is very useful. If you, as an acyclic building block, if you use a weak acid, you will end up with the hydroxycyclopentanone. It goes through the same intermediate, this and this is the same intermediate, but in difference, if you have a strong acid, you have additional water additions, and then the reaction takes the course to the livolenic acid. If you have a weak acid, then you run through this intermediate here, you can redraw so that you can see it's an enol, which can attack the activated carbonyl group and form a 5-membered ring here. And so this is what we do. This building block is the building block we use a lot. We talked yesterday about thermodynamic stability, and some people already, when we talked about how this reaction goes, or so somebody already talked about aromaticity. So note that we are converting an aromatic starting material, which is like the thermodynamic sink when we produce the furans, here into compounds which are not aromatic any longer. And so have a look for a moment. We also said this is a reaction which has 100% atom economy. So the number of atoms in the furan alcohol are exactly the same atoms which we have in the hydroxycyclopentanone. Right? It's just a reshuffling of atoms. And so my question would be, if you should make an estimate, if that reaction should be thermodynamically going from the left to the right or from the right to the left, how would you do this? And clearly, I told you yesterday, we do this under conditions of high heat, right? We have heated this to 240 degrees. So that is clearly thermodynamic control. And so the question is, what would you think if this reaction from the furan molecule to the hydroxycyclopentanone, which is a one-to-one rearrangement, it just shuffles atoms around, is that thermodynamically favored or not? And here you have 3 answers. You can just maybe even guess, but then maybe you can tell me how you come to this, guess. Okay, so we have at least 2 answers. I can always see how many people answer, because we have the number of answers here. So in the ideal world, I would get 3, 6, 7, 10, 13, 14, 15, 16, 17, 18 answers. 9 answers, 50% yield. In the paper, I would write moderate, right? Let's see, 12 out of 18, well, now we're getting 66%. Now I would almost think about maybe write good, but this is already dangerous, because I had review comments who said, 66% is not really good, right? So give me a break here. 16, now we're talking, right? So that's very good. So it's interesting what you do. So what do you do? So the one thing you realize is aromatic stability. That is something which needs to be overcome. What would you think how much this is? How much is the aromatic stability of such a furan? Let's start with a benchmark. How much is it in benzene? And you can answer in kcal or you can answer in kjoule. I don't care, because I can recalculate it. Have any idea? Well, we'll make a guess. How much is aromatization stabilization in benzene? Sorry? 40? 36. 36 what? 36 kcal. See, this is always what I have to ask when I talk to the young people. If I would talk to my generation, we would all know it's kcal, right? The young generation, I need always to ask which kind of unit you're referring. 36, 35, pretty good. So that's about a third of a strong bond, right? Carbon-hydrogen bond around 100. Aromatization stabilization of benzene is about 35 kcal. What do you think it's with furan? Is it more or is it less? It's less. Very good, right? Because it's not, you see with benzene, I can draw these resonance structures, where I shuffle the electrons around. I cannot do this with furane, right? It's more a localized system. And this is also the reason why you can do with furane a Diels-Alder reaction, for example, and with benzene, normally not, right? So absolutely. And so the furane stabilization energy is probably around 15 kcal, so it's a lot lower. So we do not have, like a benzene, we would have to overcome 35 in the furane. We have to only to overcome about 15. And now the next thing we need to do, and I find this very helpful, you will hear later on, I'm not sure today or tomorrow, you will hear about computational chemistry. So you could go now to your computer and say, computer, please let me know. You do the starting material, and it's very nice because it's an isomerization. So you don't need to worry about adding additional things. So it's a very good example for looking at the computational chemistry. So you could do this. You could do this probably yourself very easily. You have, I don't know, do you have ChemDraw here and Chem3D? You could put the molecules into Chem3D and do an MNDO or an MM2 calculation, and it would give you the enthalpies. And so it would give you a guess about this. But you can also do it a little bit by hand, and that's what we also mentioned already yesterday. You can simply compare what types of bonds are changing. And if you look at this here, then what you're doing is you exchange one carbon-carbon double bond to one carbon-oxygen double bond. And you exchange one carbon-oxygen single bond to one carbon-carbon single bond, because this is now a cyclopentanone. This has one carbon-carbon bond more, but in return it has now a carbon-oxygen double bond, and here it had only a carbon-oxygen single bond. And so you need to compare this. And a carbon-oxygen double bond is about 40 kcal more stable than a carbon-carbon double bond. And the carbon-oxygen single bond is about only 4 or 5 kcal more stable than the carbon-carbon single bond. And so by going from a CC double bond to a CO double bond, you probably win at least 30 or so kcal, depends on the source where you look up the bond energies. And you're only losing, by changing the carbon-oxygen for the carbon-carbon bond, you're only losing 5. So you probably go downhill by reshuffling the bonds by about 30 kcal. And this is enough to overcome the aromatic stabilization. And so I will argue definitely that this, although I have to break the aromaticity, that this is a thermodynamically favored reaction. And that's something, if we talk about driving forces, you should remember that, of course, aromatization stability, and whenever you can form arenes, this is usually a very good driving force in chemistry. But making carbon groups, CO double bonds, is also an extremely strong driving force because the carbon-oxygen double bond is so stable. And we all know this because when we burn something, what do we get in the end? We get carbon dioxide, right? So we get 2 of these carbon-oxygen double bonds, and this is why we always have that thermodynamic driving force here in this reaction. And so that's very good, and I'm not sure if Dr. Sakar will tell you a little bit more about dearomatizations, and I know some of you have this photochemical dearomatizations as projects in their PhD, and there it depends a lot. It becomes a lot harder if you do it on a benzene or if you do it on a heteroarene like a furane, and to do this type of chemistry. Okay, so again, I would suggest simply keep this in mind, that analyzing which bonds are changing is a very powerful tool to give you very quickly an idea about if your reaction should be favored or if it is not be favored. Still, it might not go, right? Because the kinetic barrier might be very, very high. Right? A very good example is like if you form from graphene, if you make diamonds, right? Again, the diamond is thermodynamically much more stable, but the activation barrier to go from graphene to diamonds is very, very high. Okay, so I told you about this is the compound you can be making, and we find that this is actually a pretty useful compound. I'm not going to tell you how we do this, but we can do the resolution. We are making it from the furan in a racemic way, but we can run a kinetic resolution to make these compounds enantiomerically pure in a very good way. And here's one strategy which we would apply, and especially since we were aware that such cyclopentanones, which have such side chains here, are very prominent drug molecules. And so this molecule down here, which has this abbreviation TEI9A26, this is actually in clinical phase 3 for anti-cancer. And so the one thing we can do here is, you see, of course, it's an alpha-beta unsaturated carbonyl compound, so that should undergo Michael additions, right? And you also could have asked you, but I think it's too easy, right? You can ask yourself always with an alpha-beta unsaturated enone, is it adding on the carbonyl group or is it doing the conjugate addition, right? And the typical thing is, this is the hard center, this is the soft center. If you would use a Grignard compound alone, you would add on the carbonyl group. But if you do it in the presence of copper, you're forming the cuprate, and the cuprate is soft, and so it does the conjugate addition. And so this molecule is doing something, I think, very interesting. These type of molecules with a group which was not a Bohr group here, but a TMS group, these are very well known from prostaglandin synthesis. Noyori pioneered these type of molecules for the synthesis of prostaglandins. But there, this hydroxy group would stay. Now we have, by making a Bohr group, or PMP is a phenol, it's a pyrimethoxyphenol, this becomes a good leaving group. And this is doing something quite interesting. So we can do the conjugate addition. We have one stereocenter here. And now the conjugate addition takes place trans from this group. Makes sense, right? An O Bohr group, that's pretty big, right? So we are adding from the trans position here. So this is the reason this n-butyl group, which we are adding here, or the octyl group, which we are adding here, comes from the opposite side of this substituent. And then once we add this, if you shuffle around the electrons, I will draw this in here. See, if your nucleophile comes, you add here, and I can draw all this, you have formed a new enolate, right? The intermediate you have formed such an enolate. And so, of course, this enolate will undergo reactions with electrophiles. And so you can introduce a second side chain, which we do here, and the electrophile we are using is an aldehyde. And so the moment we do this, we are generating such an addition product. And now what we found is interesting and very useful for us is that this alcoholate is able to abstract to make the other enolate over here. It's abstracting this. This one gets protonated, makes the enolate over here, and this will throw out the leaving group. So we are regenerating the cyclopentanone here. Let me go back to the laser pointer. So we're regenerating the cyclopentanone here because we're eliminating this in the end. So this is a case where you have a stereocenter, you have a control from this stereocenter of the initial addition, and I'm not going to go into this one here. This goes by a Zimmermann-Trexler transition state that is also very well controlled here. But then you're losing the stereocenter by eliminating this group here. And so it's normally it would be a diastereoselective reaction if it would stay on the addition point here and this stereocenter would remain. But now, because we are losing the stereocenter, it's an enantioselective reaction. And it's also diastereoselective in the way that the nucleophile comes opposite from here, but then the electrophile comes opposite from the nucleophile. So it's a very well stereo-controlled reaction where you're setting 3 stereocenters and you're regenerating the cyclopentanone. And so we did this for a number of examples, and it gives you very, very pure products. We did this especially for this drug molecule here, which we could get with a virtually perfect enantioselectivity and diastereoselectivity. And just comparing the optical rotation, the purity of the geometric isomers and enantioselectivity was much higher of what was previously reported by other groups was previously reported in the literature. Here's another thing you can do. You can add nucleophiles. That's what we did here. We added a cuprate. But you can also add radicals. And this is something we need to talk today, probably start, maybe not, but at the latest tomorrow when we talk about photoredox catalysis, we will talk a lot about radical chemistry. And also radicals have the very good property that they can add to double bonds. And depending on the radicals, we will also have to talk about the type of the radicals. But some radicals, like the radical, this diphenylmethylene radical, adds very, very well to alpha-beta unsaturated systems. And so we have been able to start with this molecule. And when we add the cuprate, we got this molecule. This is the reaction I just showed you. We are adding phenyl minus, and the EE stays. It's from 99%, and here we still have 99%. Now here we are adding this radical, and you can see that the EE drops from 99% to 96%. That might seem small. We talk about this in a moment. But also keep in mind, look at this. Here we are just adding a phenyl minus. Here we are adding a pretty large radical. Still, the selectivity goes down. And so my question would be, do you have a rationale? Can you explain why radical additions might not be as selective as an ionic addition? Right? The phenyl minus, the cuprate, that was ionic. And then in the second step, I added a radical, and why is this less selective? I can go back here. So here you see again the two reactions, and let me see, is this showing? Oops. Okay, I need to recheck my. So it should still be open. Okay, but I don't see, here it is. So let's see what your idea here is. No idea so far. Is it not working? Should work now. Yeah. Okay. Okay, so now we're getting more and more answers. Okay, so the one thing I didn't really have here on this slide is I didn't have the temperature that this was run. And you're absolutely right. This is by room temperature. This was by 0 degrees. So typically, as we all know, lower temperatures make reactions more selective. But the other aspect, which most of you liked here, is what we know as the Hammond postulate. And the Hammond postulate tells us something about early and late transition states. And radical reactions typically go through early transition states because they are very reactive intermediates. And so an early transition state means that the radical to the reacting center can still be very far away before it reaches the transition state. And so in this way, if this is my substrate and this has a substituent which would like to say, hey, I'm a substituent up here, please come from down, the radical is still very, very far away and might not feel this. In an ionic reaction, it's a later transition state that the substrate is much closer already with the reagent, and so it feels much more the influence of the stereocenters in there. And that is typically one of the reasons it's much harder to control diastereo and also enantioselectivity in radical and then especially in photoreactions. It is possible. I will show you examples for this, but it is generally more challenging. I showed you that we went, and as I say, we added a very big radical. The yield, the EE drop, was 99% in the starting material, and then it dropped to 96% EE. It sounds very little, but how much is it really? How much more selective is 99% EE against 96% EE, right? This is always the scale we are using when we do asymmetric reactions. Okay, here we go. See, I said yesterday, the younger generation cannot calculate any longer, but you do very well. You do this very good here. At least I should say, half of you is doing this very well, right? Okay, yeah. So 99% EE, what is it? That's 99.5 to 0.5, right? So that's 200 to 1. And 96% EE is 98 to 2. That's about 50 to 1. So we go from 200 to 1 to 50 to 1. So 99% EE is about 4 times more selective. So this is a very deceiving scale, right? It looks so little. You go from 90. If you would talk about the yield and you would say 96% yield, 99% yield, you would say that's probably operator, right? I had a good day. I had not such a good day, right? I did the workup very carefully, or maybe I lost something. I didn't do the distillation or chromatography so well. But the EE scale, especially if you reach 90% plus, is very deceiving, and that the selectivities change dramatically if you even just go up 1 or 2% of the EE value. And you see this here. You have 3%, it essentially looks like 3% EE, but you have gone from 50 to 1 to 200 to 1. Okay, so very good. So we are all aware of this. I'll show you one more example. I'll show you now an HIV protease inhibitor, which we synthesized by the radical addition to this cyclopentanone. And these radical, these type of cyclopentanes, which has such furan rings annulated, there are many natural products available here. And so that was a target structure which we thought we could make. And here is what we are doing. I show this to you in the overall reaction, and in the photocatalysis section we will talk about this more. You can generate radicals from carboxylic acids by oxidizing the carboxylate. So you have a CO2 minus, you take with the photocatalyst, you convert the carboxylate to its corresponding radical. All right, so you go from the carboxylate It's a very typical way to make radicals by a one electron oxidation. And this is what this photocatalyst, we will see more about this when we really talk about photocatalysis, can do. And it will convert the carboxylic acid, the carboxylate, to the radical. And these radicals, such carboxyl radicals, will very rapidly eliminate carbon dioxide and make the radical, make an alkyl radical. And that is something which is very useful, because now again this alkyl radical can do the addition onto the enone system. And then, as I've shown you, overall, pretty much in the end, we are also, like in the ionic case, we are going to eliminate this group here. And after the addition, so we are forming, after the radical addition, we are reforming the cyclopentanone. And so what we have done here in addition, you see the types of carboxylic acids we have used. They have an extra nucleophile here. And so this nucleophile then can rebind into the cyclopentanone. And so you can get, in one step, you can, onto the cyclopentanone, you can form a new tetrahydrofuran ring onto the cyclopentanone moiety. And this is something we utilized, and this is something which worked very well. And this is then something we have used indeed to synthesize these type of protease inhibitors, which were not invented by us. They were invented by a group in the US, but by an Indian scientist, Professor Ghosh. I've never met him personally, but I think he's in Indiana University. He has invented that, but he is coming from India. And these are fantastic protease inhibitors. So look at this. This is the structure, and you see here is this ring system, which is very decisive, and we have been able to synthesize this, starting from an amino acid, making the radical. So we are making this radical, the radical adds. We are doing the elimination, and then this hydroxyl group will rebind again into the cyclopentanone. So in one step we are able to do this. And my co-workers, they were very eager to actually make the compound, because we could have stopped here. That would have accomplished the formal synthesis. But they said, hey, let's make it. And so they made both of these compounds. And look at these activities. Picomolar. That's amazing. Right? This is really, I've never, and then single-digit picomolar. Typically, when we evaluate drug activities, we are very happy when we are in the nanomolar range, and even double-digit nanomolar range. But single-digit nanomolar range is fantastic. But here we have single-digit picomolar. So that is amazing, and a really fantastic activity. See what has happened here. In the radical addition, now we are adding a smaller radical. We started here, I've written it, we started with 99% EE. We are now down to 86. It's DE now because we coupled in the end a second molecule here with the chiral amino acid. So that's why we go from EE to DE. But still, we go from 99 to 86. And in the other diastereomeric series, we go from 99 to 91. So now you suddenly see 99%, we talked about this just a moment, is 200 to 1, 91%, 90% EE is only 95 to 5 any longer. So now we are down to about 20 to 1. 86, we are down about 10 to 1. It's still very good selectivities, but it simply shows you again this idea that the radical goes through a early transition state, and they are not therefore influenced so much by that inducing center here. Okay, let me tell you about another dearomatization reaction, and that is something which we also like a lot, and I would like to talk with you some more. You can do a cyclopropionation on these furanes. And you can do this, I show you in a moment the reagents you do, and you typically do this, and you will be getting ester groups here. You can also get two substituents here. This works very well, and you can make such bicyclic compounds in one step, and you can make a diastereos and enantioselective selective. And these are compounds which we feel are very, very useful in upgrading, making a more valuable compound from something as inexpensive as a furane. Because this molecule which you have here is of course chiral now. We start with an achiral furane, but it's of course chiral and has 3 stereocenters. So you have the opportunity for doing asymmetric further functionalizations. And it has a very distinct convex and a concave phase. That is, again, a concept which everybody should bear in mind, because we are making very often cycles. And if we have 2 cycles which are 5-5 or smaller, in our case we have 5-3. If we start having 6-membered rings, it's not so pronounced any longer. But 2 5-membered rings, I said yesterday also, 2 5-membered rings, you can only make a cis junction, you cannot make a trans junction. 5-5 and smaller has a very distinct convex and a concave phase. It's like a coffee cup, right? And if you do anything, let's say, to this double bond, it will come from the convex phase, because onto the concave phase, the reagents cannot reach. So any type of double bond functionalization will occur from the convex phase and will set 2 more stereocenters. So in 2 steps, from a very cheap furane molecule, you will be able to set 5 stereocenters in this reaction. I will also show you that you can make cyclopropanes itself, not bicyclics, because you can utilize this double bond in different ways. For example, you can cleave it by ozone, and then you get an aldehyde functionality and an alcohol and amine functionality, and you have monocyclic cyclopropanes. But you can also utilize the chemistry of an enol ether or an enamine, so you can introduce electrophiles here. And then again, one very important aspect of such cyclopropanes is that cyclopropanes which have a donor and an acceptor substituent, so the donor is an oxygen or nitrogen here, from depending if it's furane or pyrrole, and then we have an acceptor here on this 3-membered ring. So that donor-acceptor relation makes these type of makes the cyclopropane bond very easy to break, right? Because we are having the lone pair of our heteroatom here. If this goes in, and then this bond breaks to the acceptor, you see the negative charge is stabilized on the ester group, so you make essentially an enolate, and then the donor gives the lone pair to stabilize the carbocation, you go here. So that is a very broad, and many people have used all kinds of donor-acceptor substituted cyclopropanes in order to activate, to break a cyclopropane bond again. I will show you also a little bit about radical chemistry, that you can also break the other bond. And then actually a project which was a lot of fun in our group, but which I thought is very useful, is you can also break the central cyclopropane bond. And that is useful because you are expanding a furane into a pyrene, or you're expanding a pyrrole into a piperidine. And there are not so many chiral puro compounds like piperidines and pyrroles available, and so that is very useful that you can start from a furane or a pyrrole in order to do this. So I will show you a number of these reactions. So here's the typical cyclopropionation we are running, and you can again ask yourself, is that thermodynamically favored or not? And if you look at this, we are using a diazoacetate, a diazoester. Could have drawn this, but I'm sure you have seen this already. Could have drawn this with the nitro group here as well, with the nitrogen group here. And so this very easily cleaves in the presence of metals. It cleaves off the nitrogen, and you get the reactivity of a carbene. If you do this in the presence of metals, it's probably not a free carbene. It is probably a metal carbenoid. Right? So the carbene gets stabilized by the metal, and this is why this is doing this so well. And so here we are able, again, to do a cyclopropanation. We are breaking the aromaticity, and moreover, we're making a very strained ring. So ring strain is another concept. So I said earlier, what drives reactions? Aromaticity drives reactions. Reshuffling bonds to make more stable bonds drives reactions. And ring strain, especially release of ring strain, is also a very strong driving force for reactions. Here we are putting in the ring strain. How much ring strain in a cyclopropane? Does anyone know? What are we talking? Give me a number. You see, there's always a thing. I don't know if you guys have oral examinations. In Germany, we have a lot of oral examinations. So if I ask the question, then there are two possibilities, and you don't know it. If you know it, it's the easy way, right? You give the answer, everybody is fine. If you don't know it, then there are two possibilities. I ask the question, and you look at me, and I look at you, and we look at us 5 minutes in silence, and then I decide you don't know it. But the alternative is that although you don't know it, you start engaging in a discussion. And you say, okay, so let's think about this. Should it have be a ring strain at all? Should a cyclopropane be ring strained? What would be your answer to this? Sorry? Yes, but why? You see, this is exactly the point. So you would say, yes, a cyclopropane should have ring strain. And then I, as the examiner, so now we're starting a dialogue. And I would say, why? Why is this? And what would be your answer? Why is this? The bond angle in C as in an sp3 carbon usually is how much? 109 degrees. It's a tetrahedra. And in a cyclopropane, 60 degrees. Hey, so we are bonding significantly the cyclopropane. So it makes perfect sense that the cyclopropane should have ring strain. And then you could say, but then the experiment must measure this. And I would be happy with that answer because I don't really believe in memorizing too many numbers. If you do chemistry like I do 30 years now, somehow I remember it, right? Okay, that's okay. But you see, you need to start a dialogue in such a situation and not just say, I don't know it and I could give a number, but maybe this number is wrong and so on. You need to start discussing. So cyclopropane ring strain is about 27 kcal per mole. That's quite a bit, right? It's not as much as the aromatic stabilization, which we talked in benzene of 35, but it's certainly more than the aromatic stabilization in furane. So we are breaking the aromatic furane, and we're making a 3-membered ring. So overall, this sounds pretty uphill. And this is the typical way what we are doing. We're using a high energy reagent because this reagent, when it forms the carbene, is losing nitrogen. And that's probably the most stable leaving group which we have on the planet. So this brings us the overall reactions downhill because we have a very exothermic step in there. And that is typically something which we do in chemistry. We use high energy reagents in order to make reactions going where from the normal starting material to the product, which might be thermodynamically unfavorable. And I will tell you tomorrow, the day after tomorrow, something about what we like to call, it's actually not even us who have coined that term, uphill catalysis. Because that is something, instead of using a high energy reagent, you can also use light excitation. And so if you want to do a thermodynamically unfavored reaction, this is my starting material, this is my product, if I want to go from here to here, so either I have to use a high energy reagent, but I can also use light to bring my starting material into an excited state. So now suddenly from this excited state to the product, it's downhill. But overall, you have driven a thermodynamic uphill reaction. And I think this is very attractive because if you can do this by light, by an earth-abundant energy source, you can drive reactions which should be thermodynamically not possible. And that is something I think is very, very exciting. That is one thing I believe future directions and photocatalysis. In the moment, we are really happy that we can do a lot of photocatalytic reactions where we generate radicals and then do reactions. But I think this concept that you can actually use the light energy to reach a higher state from that state, a reaction to the product is exothermic. But from the starting material, look from the ground state, it would be endothermic. I think it's very attractive. It's a very important research direction. So look again what we are doing. So we are having here these very high energy compounds, diazoacetates. I tell you in a moment, maybe you also know how to make these. We do this with a copper catalyst, and we do this with chiral ligands, and these are very famous chiral ligands which are used a lot for copper. Bisoxazoline ligands, pioneered by Dave Evans, Masamune, Pfalz, three chemists more or less at the same time, made these type of ligands, and they are very, very easy to make because essentially it's an acid chloride which you need to condense amino alcohol. And the amino alcohol, of course, chiral pool you can get from the amino acid. So it's from the amino alcohol and then condensing with the acid chloride. And we have an acid chloride which has two acid chloride functions. It's a single step, and you can make these type of ligands very easily. And then depending on the chiral groups you have here, you can have that's depending on the amino acid you use. Very inexpensive. It's valine. More expensive are the tubutyl leucine variants, but you can make these type of compound, these ligands very nicely. And copper is coordinating very well with them, and then this way you can make a chiral metal carbene of this type. This will then add to the furane, and you see it's an asymmetric reaction because the carbene can attack the furane from the top, or it can attack it from the bottom, and this gives you enantiomers. And then in addition, the reaction is very diastereoselective. You see the ester group is on the same side like these hydrogens. And then it's also enantioselective, diaregoselective, that it reacts on this double bond, and if you have substituents here on the other side, it will react on this double bond. I could actually ask you why this is. All right, so you see, I choose now a furane which comes from these renewable resources. Okay, this I can need to remember that I cannot see this. So we are having the furane molecule here, which has the ester group here, and this gives you this stereochemistry and this regiochemistry, in that it adds to this double bond, and it does not add to this double bond. So what would be the concepts? Last question before the tea break. What would be the concepts you would like to use to explain this? Let's see if anything is coming up here. Anything coming up here? No. Zero answers so far. And again, you need to analyze these type of reactions, even if you don't know it, but I think some people are typing something, maybe it's not coming up. It's almost tea break. Okay, here you go. Sterically hindered. Very good. Let's see if something else is coming up. Hindrance, hindrance, hindrance. Very good. Okay, so you guys like steric. Here's one very important sentence you need to remember. Again, if you're getting asked, do you have oral exams? Or you will do everything is written? How is it? Do you have ever any oral exams at all? No. PhD defense in the end? That's oral, right? At the latest step. But sometimes even in a written exam you might do this. Whenever you get asked why is something, like why is the reaction taking place like this? Why is it doing this? The first sentence you want to write down is, there are steric or electronic reasons for this. You don't need to look at the problem. This is always a good start. Steric and electronic reasons. And then you start analyzing steric and electronic reasons. But the first sentence, that's always the concept how you want to approach this problem, is to say this. And so, let's see. Steric reasons. Very easy, right? This is a more sterically hindered double bond than this one. Absolutely. I would completely agree that this is going to do this. If you think about, the ester is electron deficient, makes this double bond electron deficient. But what does it mean? Does a carbene wants to react with an electron deficient or with an electron rich double bond? So I think there's very good analysis, whoever wrote this, saying this double bond is less electron rich than this one because I have a direct substitution by the inductive effect which might pull electrons. What about a carbene? Is that typically electrophilic or nucleophilic? And you have heard, probably both, you have heard about nucleophilic carbenes, but a carbene which you get from the diazoester, which doesn't have any donor substituents on there, it's an electron deficient compound, right? Because it has only 6 electrons on carbon. So it is an electron deficient compound, and electron deficient compounds preferentially want to react with electron rich systems. So in this case we have both the steric argument as well as the electronic argument would make the prediction that you should get the reaction on this side. Why is the ester group oriented on the same phase like the hydrogens? What's the reason for this? Because the reaction is diastereoselective. We are not trying to explain the enantioselectivity, if the carbene has attacked from the top or if it has attacked from the bottom. But why is the ester group on the same side like the hydrogens? Sterically hindered. Now we need a little bit more details on sterically hindered. I go back and show you when we started, look at this. This is the product. And you see that the ester group is oriented on the convex phase of that bicyclic system, right? So we have the convex phase and we have the concave phase. So it's like this. And all the substituents have a very strong tendency, if there is a choice, that the larger substituents will go on the convex phase. Again, this is a very important concept to remember when you talk about stereoselective reactions, because very often we do functionalization on ring systems. And then if you have convex and concave phases, the driving force for putting substituents not into the concave phase is very, very high. And I will show you in the second hour, I will show you a pretty impressive example for this. Okay. T? Okay, guys, you all deserve some tea, right? For me, it's so much easier because I do all the talking, so I'm not falling asleep, right? You guys need to have a coffee. Okay, so then we make tea break and then we come back here. Discuss a few other things with you. It's okay? It's okay? Okay. So, we talked a lot about renewable resources, right? So the furane, we all agree now, is renewable resources. What about this diazo compound? Is this a renewable resource, or is that, and that comes to the question, how do you actually make diazo acetates? Is that how would you look at the sustainability of such a cyclopropanation? Okay. So we have a few mixed answers. I think we have already agreed that the furanes are renewable, right? So that is the thing. Diazo compounds indeed are hazardous. That is, whenever you work with diazo compounds, that is something you need to be careful with. And especially it depends very much on the substitution pattern on such a diazo compound. We can draw a few things in just a moment. And to be aware of that, because they release nitrogen, they are potentially explosive. So industry is a little hesitant to use them, although there's at least one process I'm aware of where they use diazo compounds in batch to make about 370 kilograms of a product. So it is done on scale, not on ton scale. And again, there is this big debate about or the question how safe these compounds are. And we definitely would like to see other possibilities to make carbene precursors for cyclopropanations where we might not use diazo compounds, or where we would be able to using diazo compounds from generate them in situ. But indeed, maybe the good news is they're indeed coming from a renewable resource, because let me make a new slide. Let me just explain this. So the synthesis and especially of the diazo esters, you can do on a very good scale starting from glycine, right? Glycine amino acid, and so here it's glycine methyl ester already. But the amino acid behind this is glycine. And that is, of course, produced in ton scale, because it's also used as a food additive for animals. And so we do we definitely have a lot of glycine. And what you do is you do a normal nitration with sodium nitrate, like you would do a diazotation on an aniline. It's the same reagent. And then this way, I'm not going into the mechanism, but I would like to draw the structure. This way you do the diazotation, as I say, same mechanism as you would do it on an aniline. And there are a number of ways you can draw these resonance structures. And so here is one other way, and this is why you typically draw the structure with the double bond where you just say N2 here. And the one thing to realize is that in this resonance structure, so you see that there is a negative charge and this is stabilized by the ester group. Because you could draw a resonance structure which looks like this, right? And so therefore the diazo compounds which have electron withdrawing substituents on that, like in this diazo esters, are normally quite stable, and you only can decompose them in the presence of metals. But this diazoacetate you can even distill. We never do this in our group, but it's quite stable. This is actually quite in difference to diazomethane itself. See, this is diazomethane. If you have no substituent on there, then the negative charge, the carbanion, is not stabilized. And so if you ever should work with diazomethane, you need to be extremely careful because you cannot have any metal contaminations, but you cannot even have scratches. So normally when you would use diazomethane, you have to use Erlenmeyer flasks, which do not have joints, because the joints already are too rough. They might explode the diazomethane. And you need to use new Erlenmeyer flasks, because if you have an old Erlenmeyer flask where maybe you have scratched with a spatula on this, it also makes the surface too rough, and that might also be a potential explosion. So it's a big, and if you evaluate how hazardous diazo compounds are, it's a big difference between different diazo compounds. It depends very much on the substituent. For diazomethane, there's been now an alternative which people advertise a lot because, and this is the diazomethane with the trimethylsilyl group on there. This is something you can even buy. It can be shipped and everything. Again, this is much more stable because of the alpha effect of the trimethylsilyl group, which stabilizes a group alpha to a carbanion, which stabilizes a carbanion in alpha position. And this way these diazo compounds become much more, this diazo compound becomes much more stable, and in a later step you can very easily replace a trimethylsilyl group by a proton, just by hydrolysis. That goes very easy. And so this is nowadays the safer alternative. And that is what we said in the first hour, the green principles make chemistry safer. This is again a pretty good example that in organic chemistry especially we look a lot for alternative reagents which can do the same but are a lot safer. And that is true for this. And then the diazoacetates which have an ester group, they are actually quite stable, and you can do chemistry with this. And I show you, because we are running over, I show you a little bit more chemistry. I will not go too much in detail, but besides copper, you can also use rhodium catalysts to do this, the rhodium 2 catalyst, and this is especially chemistry you can see from the Davis group in Atlanta, where we have a collaboration with. And so again, from the point of sustainability, rhodium is actually not good news. Copper is a lot better, but the rhodium catalysts are so active, and you see this here, they do an extremely high turnover number in the catalytic cycle and very, very fast. And therefore, it is acceptable to use rhodium instead of copper. And when you see we have another diazo compound here. This diazo compound is even more stable because it has another substituent which can stabilize the negative charge on the diazo carbon, and copper will not be able to easily release the nitrogen from very stable diazo compounds. So I show you, I will not show you, I have to skip over a few things, because otherwise you will have no lunch, and that's something I don't want to do. And I would like to show you a few more concepts, and I'm going to do this by looking at this this compound. It's a natural product. It's an antibiotic, xanthine, and that was again made when it was isolated and the biological activity was released. It was found that it is very, very interesting because it showed antibiotic activity against this MRSA strain. And I'm not sure if you have heard about this, but this is the hospital strain. One of the biggest dangers these days when you have to go to a hospital for surgery or whatever is that you contract an infection. And this is one strain of bacteria which is in particular very prominent in hospitals, and almost no antibiotics help against this. And so that's, as I say, this is very often it's the bigger danger to get such an infection than the surgery itself. And so this compound was shown that it might be good against this strain, and so that's why we became interested in this. And I show you just a few ideas what we make. We are able to convert the furan molecules into such lactones which have another aldehyde group. And if you want to go through the slides, then through the handouts, there's the way we do this. It's in the slides, but we are not going to cover this. And then, in order to get the 7-membered ring on here, which we need in the product, ultimately what we do is we do a Grubbs metathesis. So that again is one of the corner developments in organic chemistry. It got the Nobel Prize in 2006, the ring closing olefin metathesis. I'm not sure how familiar you are with this, but the idea here, let me briefly mention the reaction, is that you have, if you have a diene system and you have these, and you see again, it's a carbene complex, but it's a carbene complex with ruthenium, and it's a ruthenium 2 complex. And these complexes are able to do a reshuffling of the double bonds, and this way form rings. And the way the way they can do it is that the ruthenium carbene can do a 2+2 cycle addition, and then it can do it forms in one way the bond, and then if you break in the 4-membered ring which you get out of this, if you break the bonds in the other way, then you see you releasing ethylene and you get the carbene on the new center, and then you can do this again, right? Then you can do this with the second double bond. The Grubbs ring closing metathesis, Nobel Prize in 2006, has really contributed that we rethink the way how we make rings, because this has become such a powerful methodology, and therefore is being really applied. And when it was developed, it took only a few years until the Nobel Prize was awarded for this technology. And so we've been also using this. You see, in our example, we have a double bond here, and we have a double bond here. And so if we chop off, should have stayed with my pen. You see, we are chopping off this part, and then if you count this, 1, 2, 3, 4, 5, 6, 7, then we are forming the 7-membered ring, where we have the double bond now between 1 and 7, right? 1, 2, 3, 4, 5, 6, 7. And so this was the ring system which we wanted to make. And now look at the target compound we have. This is why this is the step I would like to show you. In the target compound, we have a methyl group here on this position. This would be essentially this position here. And it will have to be introduced in a stereoselective way. And we would have liked to somehow switch the double bond, right? Because you can also see that the double bond has been switched here. And then we envisioned that the side chain, which we need here, we can convert the ester group to an aldehyde and then do Wittig chemistry. So we thought that was easy. But the challenging aspect was, can we install the methyl group here and move the double bond? And it has to be done stereoselectively because we needed the stereocenter. And so the way we wanted to do this is we wanted to do an allylic oxidation. So this carbon, we wanted to do an allylic oxidation because once we have this allylic oxidation, if we make a better leaving group, we thought we can do a nucleophilic substitution like this in an SN2 prime type fashion. Here's another variant of an SN2 reaction, and the SN2 prime reaction is also going anti this inversion of stereochemistry like the SN2 reaction is going, right? And so the challenge for us is we thought if we can accomplish this, then we thought that this might be a good strategy then to finish the molecule. And my question is, would you have confidence that you can, with an allylic oxidation, can do this regioselectively in the way that you can install the hydroxyl group there, and also stereoselectively? And here's something we learned, and that is, the question is, can we control the diastereoselectivity? You see our chiral information, the stereocenters which we have, excuse me, are here. So the question for us was, can we use the stereocenter to control the stereocenter where we want to introduce the allylic hydroxyl group? And so I would like to ask you, if you think about models which we have for predicting diastereoselectivity, what do you know? Are there any concepts and models, rules we use for predicting diastereoselectivity in reactions? What are famous and important concepts? I need to hurry up a little. I keep this, but I will need a new slide for drawing. Yes, so Cram's rule, good point. Evans model, also good point. The Evans model is already something where we try to control enantioselectivity, but you definitely Cram, Falcon, Arn, that's a good model. DFT is of course how you can then predict it, how the reaction goes. I would have thought maybe about another model as well, the Zimmermann-Traxler type model, right? That's also very good. And so these are typical models. So Falcon, Arn, or the Cram-Chelate, these are the two models we typically apply. This is something where we have a stereocenter next to our prochiral center, right? So if we treat this with a nucleophile, then typically we can get two diastereomers and the Falcon, Arn and the Cram-Chelate model will help us to predict this. And this is a typical model for a 1-2 induction. And then the Zimmermann-Traxler transition, the Zimmermann-Traxler model, this typically helps us to understand, for example, how an enolate will react with an aldehyde in an aldol reaction. Because there, let's say we have a lithium base here. Because there we can have our enolate. So the enolate geometry is very important. Then we arrange this in a cyclic way, in the way that it's sterically most favorable, so we put the aldehyde substituent into the equatorial position, and then we can predict the relative stereochemistry between these two centers. And so again, this is a model for a 1-2 induction. And then somebody wrote the Evans model. So if you make this chiral with an auxiliary here, you might control, you see you can form two enantiomers of the syn product. And with this chiral auxiliary here, you might actually control in addition the formation of the absolute stereochemistry. But these are typically models for 1,2 induction, and that is what we know, that a stereocenter might influence a prochiral center on the next atom, 1,2 induction. Very few examples are known for 1,3 induction. One of the famous ones I also mentioned here briefly is that if you have, for example, an aldol compound, there, if you do a reduction with hydride in the presence of some metal cation, here you can utilize that the metal might, similar to the creme chelate model, might form a chelate here, which now might direct the nucleophilic attack, and there are again models, from the opposite side of the stereocenter. So that is really one of the few models I know where you have an induction from a center which is not directly next to your reacting center. And so for us, this was I see there's some more things, okay, but let's take that. So for us, you see, what we want to achieve here is also a 1,3 induction, 1,3 stereo control. And so for us, we thought that is probably not possible. And now I show you how lucky we have been. And what we did is, I go over the next question because we are getting too much behind. What sometimes helps very much is if you have an X-ray structure from your starting materials, because with an X-ray structure you can analyze very carefully conformations. Very often we use an X-ray structure because as organic chemists we want to know if the composition of our molecule is right. But in this case, we've been able to use the X-ray structure, and the first thing which was surprising for us is that this 7-membered ring, which we thought might not have very defined axial and equatorial positions, that this is actually wrong. You see, we had an axial hydrogen and an equatorial hydrogen, although it's a 7-membered ring, it's not a 6-membered ring. In the 6-membered ring, of course, we know it very well, right? We have chair type, the preferred ring is, 6-membered ring is a chair, and there we have very defined equatorial and axial positions. And we were not sure how that would be in the 7-membered ring, and especially we have a double bond in the 7-membered ring. But it turned out that the 7-membered ring had the same type of features, so that we had an equatorial and an axial hydrogen. And that was really the way that we had this equatorial and axial hydrogen is being influenced. Of course, the ring is folded by the ring next to it and by the stereocenter which we had. And then we made use of a reaction which is the so-called Rayleigh oxidation, where with selenium dioxide you can oxidize allylic positions. So you have a double bond and you can attack an allylic position. You see we have one allylic position here, but we have also one allylic position here. But the rule is that because it's a concerted reaction, it will always attack the hydrogen next to the substituent you have on the double bond. Because this is how the reaction goes, is because the selenium gets, in the first step, gets introduced, adds to the double bond, and it will do this for steric reasons on this carbon, and it will not want to do it on this carbon. You see, if it wants to attack this allylic bond here, if it would have attacked this allylic hydrogen here, then the selenium would have to be on this carbon. And so therefore, this was regioselective, and this we would do the allylic oxidation on this carbon and not on this carbon. And we would selectively do it on the axial hydrogen, because then this way the geometry of that concerted reaction, you see the selenium can only attack from the top or the bottom, and if it attacks from the bottom, the axial hydrogen is ideally located to be abstracted. And so then this is the first step of this reaction of the allylic oxidation, and then in the second step, the oxygen will attack on that carbon here. I should have rotated it, so the oxygen of the hydroxyl group will attack here and release and create an O-selenide bond, which is hydrolyzed to get this hydroxyl group. So for us, this was a very lucky day because, and you can see in very good yields, as a single regio and diastereomer, we have been able to do a reaction very selectively, which we didn't expect. The reason I show this to you is I just want to emphasize how useful it sometimes can be if you have X-ray structures and analyze conformations in order to do this. And then the rest of the chemistry was very easy. It's exactly as I said. We make a better leaving group out of the alcohol, an acetate group, and then we could all kinds of nucleophiles. We could attack in an SN2 prime reaction, the allylic acetate. This is the typically sterically less hindered sp2 carbon gets attacked here, moves to the double bond and throws out the leaving group. And this way we could relatively quickly finish the synthesis and actually also make lots of analogs of that compound, which we are testing for their antibiotic properties. Okay, let me show you. There are. Let me see if we do some of this maybe tomorrow. We have another 15 minutes. Okay, I show you one more example, and then I show you probably tomorrow a few more examples. This is another natural product, pyrrolite, and that also cost a lot of it. We have until 12:15, Sangeeta, is this right? Sangeeta, we have until 12:15? 12:15, okay, so we do one more natural product. This is pyrrolite, and pyrrolite is of big interest because it is similar to the structure and the properties of these very complicated ginkgolites, but you can see it's a much easier structure. It's endemic in the south of China, comes from this plant, and it was isolated and actually quite good from 1.13 kilograms from the bark of the roots, but that's always a problem if you have to go to the roots in order to isolate this, and they could isolate 8 milligrams, right? And so when we started this, there were racemic syntheses available and one synthesis from the chiral pool, and we also wanted to synthesize this. The reason why that was so interested is it's a selective inhibitor of the aggregation of thrombocytes. I'm not sure if that says anything to you, but if you cut yourself, then you start bleeding, but the bleeding stops pretty fast, and that is because we are clogging our blood. Our blood, so we have platelet aggregation. Otherwise, we would bleed to death, right? But if you have a stroke, then you need to take blood thinners, and these blood thinners need to be stronger than aspirin, for example, right? Aspirin is also a blood thinner, but you have to take a lot of aspirin in order to have the effect you need after a stroke for blood thinners. So typically, do you know what type of compounds you give if you have a stroke? What type of blood thinners you have to take? You take rat poison. Sounds very scary. Let me tell you how to kill a rat. That's not so easy, because the rats are very intelligent. And so if you put rat poison, if you would just put a poisonous substance in some kind of food, then the first rat would come and they would eat the food, and all his friends were looking at the rat eating the food, and then they see the rat drops dead, and they say, hey, wait a minute, this comes because the rat ate the food. So they're not touching it any longer. So if you just have poisonous food where the rat dies immediately, you kill the first rat, but you're not killing any more, right? Because they're clever. So what you need to do is you take rat poison, which are blood thinners, and they have pretty nasty compounds, all kinds of things. And the idea there is the rat come and eat it. All the friends are looking, but nothing happens to the rat. So they think, oh great, so we also eat it. But then they go back to their house, to their hole, and then they start fighting. And then they scratch each other, and then they bleed to death. This is what you do. And that's very nasty compounds. There's a lot of side effects. And so there is a need to find more selective blood thinners, which have less side effects. And this is one of the compounds which was hailed for maybe being able to do it, because it is selective for the aggregation, to prevent the aggregation of the thrombocytes, but it has no other side effects on other enzyme pathways. And so that's why others and we became interested in this. And so here's one thing I would like to also stress about this idea of convex and concave. You go a little bit faster over this. So again, this is the cyclopropionation of the furan. Note that we're using a different cyclopropane here. It has the ester group shifted by one carbon, but it works just as nicely, and it's again also available from renewable resources. What we do here is we do a hydrogenation of that double bond. This hydrogenation, let me ask you again, can you tell me Can you tell me why that cyclopropionation is so stereoselective, and especially on which side of the phase is the newly formed stereocenter, this ester bond? Where does it go to? You see, it goes now away from these hydrogens. So what is it doing here? Okay, now we have two answers, because I told you already that the ester groups really want to go on the convex phase and they don't want to go on the concave phases. But the question is, does the ester group has a choice here? Let's go very much back to the first slide I showed you. This one. So we already have the cyclopropionated product, and so here's the ester group. That's our R2. The hydrogenation will come from the convex phase. It doesn't want to come from the concave phase. So the hydrogen is going to add from the top. And so that forces the ester group onto the concave phase. It doesn't have a choice. It has to go there. So again, always keep this concept of concave and convex issues in bicycles in mind. Nope, wrong compound. Okay. But then in the pienolite itself, you can see that it's not an ester group any longer, it's an alcohol. This is on the convex phase again. You see the hydrogen is on the same side like this one here. But in our reaction, this group here is on the other side of this one because we push it on the concave phase. We thought we probably are okay with this because now there's this high tendency, if you have such bicyclic systems, they will always try to isomerize to put the substituent to the convex phase. And this was indeed the case. When we added acid to reopen this bond here, and the idea is to open the bond, and then the ester group here gets hydrolyzed to the carboxylic acid, and the carboxylic acid bites back onto this carbon. So we're getting, again, a bicyclic system. And in this system, you can see now suddenly the group is on the same side like the hydrogens. It has migrated to the convex phase. my coworkers were very observant that actually the two hydrogens here flip, and it's not that this group flips. And the way we thought this goes is we open this up, we get the carboxylic acid group, and here an alcohol, water addition. And this might be in an equilibrium, the water might eliminate. You see, this moment we are scrambling the centers, the centers are gone. And then if water re-adds and we do the lactonization, it can go either way, and it will go in the way thermodynamically favored, that in the end, this substituent is on the concave face, so on the same side like these hydrogens. So again, there's a very strong driving force in order to make this. And so, so we could again finish the synthesis. I don't want to go too much into this, and so that all I want to say is that we are able to do this. Now here's another maybe interesting thing. Do you know how to test now if your compound has these blood, this effect of preventing the aggregation of the blood cells? How do you test this? Yeah, obviously you need blood somewhere, right? You draw blood, and then you have a blood sample, and then you give the compound, and then you see if it aggregates or not. So my PhD student, Matthias Gnan, we contacted our pharmaceutical department, which is in the same department like our chemistry department. And we said, can we do this testing? And they said, yes, but you need to come every Monday morning, 8 o'clock, and we need blood. So he had to come every Monday morning, 8 o'clock for 6 weeks, and they would take his blood. So he not only synthesized the compounds, but all the testing was done with his own blood. So that was really commitment, right, from a PhD student. Okay, so I think at this time we stop in time. I would like to show you a few more things, because we will talk about photocatalysis with radical chemistry. I would also like to go over some basics on palladium chemistry, and I will also show this on one example I have here still from our Furian chemistry. But we are going to do this tomorrow because I'm off for the rest of the day, because Deepak, I think, will do the next lecture. So thank you very much for bearing so much with me, but you will not, today you're getting a break and somebody else will do the teaching in the afternoon. So have a great lunch, and then I see you tomorrow. And somebody wanted to talk with me over a reaction. We can do this right now, and then, but then for the course, I will see you again tomorrow. So thank you very much.
Okay, so all of you can hear me, so that you are not sleep, okay? Because after lunch and then with this summer, cold atmosphere, I think you guys all will be feeling sleepy. It's my responsibility to make you, keep you awake, okay? So sometimes maybe some questions I'll throw you open so that you get off from your sleep. Okay? Okay, and by the way, how you guys are doing here? All of you are staying inside or just outside, some of you? All of you are outside, or many of you are outside? Okay, so I hope that you found some time or you will find some time to roam around inside the campus as well, okay? And that will be a good experience for you to see the things, as I said earlier yesterday. Today, here, I think till now, whatever we have learned, mostly from synthetic point of view, how you can synthesize complexes, and by applying different techniques, okay? And today we will learn something. If you synthesize something, how you know that what you have synthesized, isn't it? That is also an integral part of your learning. Otherwise, you will do something or you will make something and you will not know what you have made. So for that, we need to learn some of the techniques, which is mostly spectroscopic technique, where you will learn how to differentiate or how to analyze the things which you have prepared. Now, if you have seen the title of this, it is mostly I will be concentrating on IR and NMR spectroscopy, okay? And today we will go from the basics and then some application. And you know, in NMR you will be learning many aspects, not only proton NMR. That's why in the next class, means tomorrow's class, which is mostly on heteronuclear NMR. So today we will learn what NMR is, how NMR look like, and some of the aspect of the proton NMR. And then tomorrow we will learn about the heteronuclear NMR spectroscopy. Okay? So now before going into this topic, as you were connected from the today's morning class, that is mostly on transition metal based catalysis, isn't it? From Professor Oliver Weiser. So all of you know by now how a transition metal initiate the catalysis process. If I ask you, and while doing this, our presentation and all these things, you are free to ask me questions anytime and stop me anytime. Okay? So that's not a problem for me. So we can go around and then see things, what's going on. Okay? So that's liberty, you have it. So how a catalysis process is initiated by the transition metal, if we know, but why the transition metals are so important for catalysis, if I ask you. So what will be your primary answer? Does anybody understand that? Why transition metals are so important in catalysis? It's mostly for their variable oxidation state. Okay? Because to do a catalysis process, you have seen that it has to be an oxidation, then reduction. And if a transition metal can vary their oxidation state, then only it is possible to have that catalysis process going on. Otherwise, it is very difficult, isn't it? If a transition metal cannot vary their catalysis process. And in that aspect, you will see rhodium and iridium, ruthenium, they are the most important one, or palladiums. Now, if I bring back to your S block elements, they are also metals, isn't it? In the S blocks. So they are also metal. And they also do participate in catalysis. So will they participate in the same type of catalysis or similar type of way? So which brings to this slide where you see this, the first one here. It's an example of a typical reactions where an hydrogen and element bond is added to the alkenes or alkynes. Okay? So it's like your E means any element, H hydrogen, so that EH bond is getting added to the alkynes. So this is the rhodium catalysis process where you see this rhodium takes up this, and now you see this rhodium now increase the oxidation state by 2, isn't it? Because it made 2 more bonds with the substrate. So the oxidation state of the rhodium changed from by N+2. But in case of a main group elements, like suppose magnesium, calcium, okay, So they don't have that liberty to use that because they all don't have the d orbitals. Okay, but even though they do the catalysis process, I'm sure that you will go into some research, and this is a very fine tuning which is required to know how a main group chemistry can come into this catalysis process. Okay, so you see that they undergo these two processes. One is your sigma bond metathesis process. That means a complex will have a group which can take up the substrate, and one group will be released, and that substrate will come and attach to the magnesium or the main group elements. That means you are not seeing any change in the oxidation state because that liberty they don't have. Okay, so what we can do these two processes, either sigma bond metathesis process, like you see here, this compound, this is a magnesium butyl group attached here, isn't it? And this butyl group, when this H is taken, it is liberating as a butane. So that's your sigma bond metathesis process happened. Now this OPPH2 group gone and attached to the magnesium now. Okay, so once this OPPH2 group goes to there and attached to the magnesium, so what it does, due to the difference in your electronegativity, the bond between magnesium and oxygen gets little polarized. That means magnesium can generate a delta positive charge on the magnesium center, and that delta positive charge is required to now initiate the alkyne coordination. Other than that, it is not possible, because we have seen alkene or alkyne coordinates to the transition metal like a pi ligand, isn't it? That this magnesium, calcium, it is not possible. So it is only possible when they generate a delta positive charge. So that fine tuning you should bring into your research when you do that, because now we are going to a sustainable chemistry, and transition metals is now going to a sustainable chemistry. So we need to use these main group compounds into the catalysis or into the materials. Okay, so this is a very nice aspect I just bring into you because I will be talking mostly on NMR, IR and all. So before that, just to connect you how you can sustainably do or think about catalysis, this is one of the example. Okay, I hope that everyone got what I was about to say. If you have any queries, just say me here, okay? Or we can move forward. All fine? Okay. Okay, now coming back to this NMR spectroscopic and all, and IR spectroscopy, what are the things we are going to learn? And by the way, what is spectroscopy? Do you know when you write IR, NMR, UV, you say all the time spectroscopy. But when you write mass, do you write mass spectroscopy? Why you write metry? Why? Why is it so? Is there any difference in that? When you say spectroscopy and spectrometry, what differences you bring in? So very good. Spectroscopy means you will have a matter and the light interactions. Okay, so light means your electromagnetic radiation. So any form of electromagnetic radiation will interact with your matter to get the spectra. So that's what your spectroscopy comes from. But when we talk about spectrometry, in mass spectrometry, there is no electromagnetic radiation is coming and interacting with your matter. So that's why all the time when we write, that differentiate the things. So now IR also is a technique where we will learn how things can be like electromagnetic radiation interacting with your material, and then how this IR generates. That means where that IR electromagnetic radiation is going to be interacting. then some little diagram of your IR spectrophotometer, and then uses of IR and some interpretation of IR spectra, and finally characteristic absorptions, and then some checklist like what are the things we learned. Okay, so so if you look at this picture, so in the highlighted portions, if matter interacts with or emits electromagnetic radiation, that's your spectroscopy. And now we have the different types of energy of different frequency, from your gamma rays to radio waves, and based on this energy of that, they are going to interact with your matter. So all the energy are not going to be interacted with all the time, isn't it? So there is specific region energy is required to interact with your system. So when we talk about IR, so this is the portion where we talk about, which is after the visible region it comes in. So what it does, now you see this. So when we talk about this infrared, they are going to excite that vibrational level of energy. Okay, so if we have two electronic state S0 and S1, and between this S0 and S1, this is what this diagram is, what you have seen here from physical chemistry classes, isn't it? That diagram is called your Jablonski diagram, isn't it? So your S0 and S1, and in between these electronic states, you have several vibrational states and several rotational states. Okay, so these vibrational states is going to be responsible for your IR. I hope this much you guys know. Okay, now if you see this, the energy required for this bond dissociation, like when you vibrate a bond, that means it is going to be dissociated, and from that energy is going to be now linked to your IR energy, because that vibration or your rotation is going to be responsible for that. Okay, now IR spectrum of a molecule is going to be a very, very unique physical property and characteristics of the molecule, because from there what we can understand or what we can learn the unknown compounds, because what you have made, what it is, you have to know that. And at the end of this talk, we will see that, or at the end of this class, we will see only IR is not responsible, or it is not enough. Only IR is not going to be enough to know what you have made, but some interpretations you will get from the IR spectra. And IR information can indicate whatever things. It's a linear or branch backbone, or if the chains are unsaturated, that means whether it is a single bond or double bond or triple bond compounds are there. And is there any aromatic rings in the structure, or we will know about the functional groups. Okay, so functional groups means you will have OH, alcohol, CO, carboxylic acids, aldehydes, and so on. Okay, nitriles and all. So these are things we will know from the IR spectra. Now, very one important condition is that only those vibrations will produce, or we will see in IR, where there is a change in the electric dipole moment of the molecule. Okay, so when the vibration is happening in the molecule, there should be a change in the dipole moment. Then only that IR is going to be, or it is going to be IR responsible, or we will see the IR spectra of that molecule. Is that understood now? Without the dipole moment change, we will not see anything. That's why you learn that maybe symmetrical alkenes or alkynes, they don't show. Whenever we have an unsymmetrical one, then only we see that. Or that CO2, It's a linear molecule, isn't it? It's not going to show a symmetrical stretching, but unsymmetrical stretching is going to be responsible for the IR. And like you see these diatomic molecules like oxygen, nitrogen, bromine, they do not produce a change in dipole moment. So to know this, what spectroscopy we require? To know this, whether it's a homoatomic or it's a symmetrical one. So what is that? It is the Raman spectroscopy. So which can distinguish or which can tell that, okay, this IR or there is a vibration between the bonds. So Raman spectroscopy does not see the, what is called your dipole moment. Okay, now how these bands are going to be positions, like on which law? That's a Hooke's law, isn't it? Because when we talk about a bond, by the way, now we know the bond means a physical line between two atoms, isn't it? And when you will know more, you will see there is no physical line between the two atoms. So the bonds will be kind of an electronic interactions. Okay? Because as long as we are knowing the fundamentals, because we want to see the things. And when you want to see a things, you need a physical things to see. Okay? And when you are mature enough to see physical things, then you will think beyond of that. So like bond, what it is between the two atoms which is connected, okay, and when you vibrate the bond, that means you are generating or making some kind of a vibration of this bond, isn't it? It's like a spring is attached to something, and when you pull or push, you will see some vibration in that. So based on, or similarly, that law is applied for this IR stretching frequency to understand or where the bonds will be. So more the stronger bonds, isn't it? What we will see, you need more energy or more force to vibrate that. Okay? So this is the equation of this. The frequency is going to be dependent of force constant of the bond, and it is going to be the inversely proportional with what? The reduced mass. So we will see that some tip, like a very, I would not say very trivial, but very kind of small questions, or very quick, small tweak will be there in the questions that you will not think in that directions. But if you apply this, then you can answer those questions. So this is a thing which I have already told. Now the vibrations can be, or stretching can be of two types, like symmetric stretching and your asymmetric stretching. Like if you take a molecule of V shape, like a water molecule or CO2 molecule, then the stretching frequency can have like your symmetric stretching, or it can be one is going forward and one is coming backward. So it's like your asymmetric stretching. Okay? So, and you have one kind of a bending. That bending has different aspects also, like scissoring, okay, wagging, and all these things. But as a whole, they are called as a bending situations, as bending modes. So as it is a PDF mode, so I cannot show the things because there was some change in the PPTs. So now we will come to the some aspect. What are the factors which will affect the absorption frequency in the IR? So if you relate to your bond, what about the bond like a Hooke's law? Okay. So then you can understand, or you can explain what are the factors are going to be affecting this absorption frequency. So in Hooke's law, what are the things we had? We had force constant and we had some reduced mass. So now these two are more important factors, isn't it? So more the force will be, you will get your frequency higher, and the more the mass will be, you will get your frequency at the lower. Okay? And then after these two, you have what? Some other aspects as well, like hydrogen bonding. So how the hydrogen bonding is going to change your IR frequency? Anyone can say that thing? How it is going to change the IR frequency by hydrogen bonding? By the way, what is hydrogen bonding actually? It's a weak interaction, isn't it? It's a weak interaction because that's not a bond actually. So they are all the weak interactions from van der Waals interactions, like a pi-pi stacking bond. Okay? Like these are all van der Waals interactions or weak bonds. So the weak bonds will be between two electronegative elements and when you have a hydrogen. So there you get a kind of an interactions between your hydrogen, which is a positively charged, and you will have a negatively charged element. So that interaction is known as your hydrogen bonding interactions. Now if you have that situation, so what you are bringing, you are making that H to the element bond, what? You are making it as a weaker bond. Okay? So as long as you are making that hydrogen bond as a weaker bond, so your frequency is going to be changed. Because when you make that bond weaker, that means your a hydrogen is going to be far away from the element is attached. So the bond strength of that bond is going to be changed, isn't it? So that's how the hydrogen bonding is going to alter the absorption frequency in the IR region. Now talk about this resonance. So I think by now all of you know what is resonance is, isn't it? Yeah? Because you are now master of organic chemistry. Yeah? So the resonance means what? If you have electrons, free electrons in your system, it can be a non-bonding electrons or it can be a pi electrons. So those electrons can go from one place to another by keeping the structure same. Okay? So it is not going to change the structure. So they can go from one element, like one bond to another bond by the delocalization process. So if you have that kind of a situation, like delocalization of the electrons of non-bonding electrons or pi electrons, so that what it will happen, then the bond between the elements are going to be disturbed, isn't it? Is it understood or not? We will see the examples. So just the basis I'm talking about here. So when you have bring this resonance into the picture, they are going to affect your absorption frequency. Another one is your bond angle or ring strain. These are the classic questions you get in your MSCs or sometimes when you give your exams. Like you have a hexanon, you have a pentanol, or you have a 4-member ketones, where this CO stretching frequency will be higher and why. Okay? Or if you have a sp2 carbon, you have a sp3 carbon or sp carbon, and that is going to dictate the IR frequency. And from there we will know whether you have a sp or sp2 or sp3 carbon by seeing the IR spectra. And then definitely hybridization, which I told. Then the polarity of bonds and some external forces like concentration, temperature, solvent. These are the external forces. Because if you increase the temperature, then the vibrational energy also, the bond will vibrate in a faster way, isn't it? compared to the lower temperature. So then you will see the vibrational or the air absorption frequency is changing over the time. It's okay? Huh? Okay. So till now you are all fine? You are on the same board where I am right now? Or you have some different aspect or different thought process? Huh? All are getting along with me or not? Okay. Now, whatever the points we have discussed earlier, the factors which are going to change this stretching frequencies, we will see the examples one by one or some of them. Like in the first case which we discussed, you see the CC bonds, okay? If I see here CC bond, it can have a single bond or you can have a double bond or a triple bond, okay? So you see the stretching frequency of the CC bond, when it is single bond it is 1000 centimeter inverse, 1600 to 2200 centimeter inverse, okay? Now this single bond, double bond, triple bond, that means the carbon-carbon distances or carbon-carbon bond distances are getting increased or decreased along the single bond to double bond to triple bond. They will decrease, isn't it? That means your bond order is getting increased. So when your bond order or bond strength is going to be increased, that's why you are seeing higher frequency. Similarly, in case of your CH, if you see that, what we see that when you have a carbon which is attached to an CC bond, there you see that it is 2900 centimeter inverse, but when you are increasing to alkyne system, that CH comes at where? At 3300 centimeter inverse. So this how we can explain? By hybridizations. So what it brings to you? So your sp3 carbon and then you have sp carbon, okay? So that means sp carbon means you have sp character more there, so s character more, isn't it? So when you are increasing the s character of a system, that means your that bond which is connected to the other element, that's going to be in higher frequency range, isn't it? So if you know this, then definitely you can tell when you have a ring strain or bond strain. Now when masses of the atoms attached to the bond, you have CH bond, you just think about it. This is a typical question comes to you. You have CH bond, isn't it? And you have a CO bond. And CO is a double bond or triple bond, carbonyls. Where you see that stretching frequency in general, carbonyls? Carbonyls is seen 1700 around, isn't it? If it is an organic compound. And if you have a CH, it's more than 2900. But you have double bond and you have a single bond, isn't it? What we expect? We expected that CO should have been more than that CH. Okay, this is a tricky and trivial questions, you get it. When we are in the exam, our brain is confused and we don't know what's to be answered. But this is a very very simple way to look at. If you see the masses of the atom attached to the bond. So you have CH, that means your carbon and hydrogen, and your CO, you have carbon and oxygen. So we are not talking about the same element around the bond. We are talking about two different elements around the bond. Okay? So then, when you bring an oxygen, that means what you are doing, you are increasing the reduced mass, isn't it? So your reduced mass is getting increased. That means the denominator of here means the mu, which is inversely proportional to your frequency, is getting increased. If you think about your Hooke's law, the frequency was inversely proportional to your reduced mass. So that is going to be increased. So definitely your frequency is going to be hampered. Means it is coming to the lower frequency range. So these are very short thinking, but our brain doesn't work that time. Okay? Now let's see this CO, CS and CH which we told about. So heavier the atoms, your mu gets higher and your stretching frequency gets lower. So there are some examples of CH, CC, CCl, CBl and CI about the stretching frequency. I don't know in my next slides that is there or not, but while talking this, we have some, I think it will be there, some regions. Generally we don't see a region till 1000, isn't it? Some 800, 900. Because there are what? In your IR, when you see an IR spectra, till 800 to 900, we are not very much concentrated, isn't it? Or we don't much think about what it is there. Because mostly those are going to be the bending modes. And there are so many things are there that we cannot get a very good idea of what bonds are there. Okay, and that's why they are called what region? Your fingerprint regions. Okay. Yeah, this is the one I was talking about, your hydrogen bonding things. So you see this, the free OH comes at here, and when it is hydrogen bonded, its frequency is reduced. Not only frequency, you see that the nature of the spectra also changed. That means you are getting kind of a more broad spectra compared to a sharp one. So that means your hydrogen, which are kind of going away from the O, and this bond is kind of going to be like a more broader bond, not a narrow band. Okay, now look at this, your conjugation thing. Okay, in this conjugation what we see, this is a free ketone which comes at around 1720 centimeter inverse, but when it is a conjugate with an alkene, it goes to your 1680 centimeter inverse. So that means the conjugation has made the CO bond weaken. How? Because the electron density from this pi electron can go to from here to this pi electron, making the CO bond from a double bond to a kind of a partial double bond character, so that your bond strength is going to be decreased. Now these internal factors like your bond angles and ring strain, which we were talking about, that can be connected to your hybridization. When you have a cyclohexane ring to cyclopentane and cyclobutane, how the rings like a bond angle is reducing, isn't it? So what is the bond angle here? 60. What is the bond angle going forward? What is the bond angle in your cyclobutane first of all? It's a 90 degrees. And then here 1. Any idea? 72. And here then 60 degree. Just think about it and then answer me what it will be. And how you can tell this from your 1715 centimeter inverse to 1775 centimeter inverse. So if you are increasing from 1775 centimeter inverse to 1775 centimeter inverse, that means what? Your CS bond strength is getting increased from your cyclohexane to the cyclobutane, isn't it? Now how you can, what is this called? How you can explain that to me? Is anyone? You tell me what, if it is wrong, it's fine. Here we are just learning things, isn't it?
So bond angle and then S character is also inside the ring. So S character of outside the ring increases. That's why S character outside the ring increases. That's why the
See, when you talk about S character of the atom, isn't it? So whether it's outside or inside, it will be same because that's the only one atom there at that place. So it cannot be outside or inside. Whether the S character is increasing. So now we are in a same line that okay, the S character is increasing down the from hexane like a six member to the 4-membered one. That's why our CO bond strength is getting increased, which you have seen in your hybridizations, isn't it? Okay, so please you can think about it and we will come back there again maybe. So this already we have discussed, it is more or less similar. So now these are the all intrinsic properties of the IR what we have learned, like how the IR is going to be governed, how we can IR is generating, and how or what are the factors are going to be changing the IR spectra. Now how we record IR? Have you ever anyone seen the IR spectra? And you have done the IR spectra? No? Yes? How many of you have done IR? And what is the basis about the IR? How it is done? What you do generally? You take your sample, isn't it, to the machine first of all. And you either you do solid sample, liquid sample, that up to you based on your sample. And you place your sample in a sample holder. And have you ever seen when you are placing a sample holder, there is a very red color, like a ray goes. Have you ever seen that? No. So you will see very nice red color dot like your laser pointer. So similarly a red color dot goes, that is your IR beam. So that's your IR beam pass through. So as soon as you put your sample or place your sample, that what happens there, your IR now passing through the sample. Okay, and when it passes through a sample, that means it will show or it will interact with your bond of your molecules, and that bond of your molecule now is going to be vibrated, and that vibrations will be recorded and you will get your spectra. So for that you see that electromagnetic source is going to be bifurcated into two. So that means you are going to be reference beam and that's you are going to be your sample tube. Okay, so it's a splitter here given, split. So when the sample goes in, it will be split into two and you get to your reference beam and your incident sample. And after that, when you plot a IR, what you plot on your y-axis? Generally you plot transmittance, not the absorbance, isn't it? That's why you always see the spectra in an inverted one. But if you have drawn the absorption, then you would have seen in like an upward direction of your spectra. And why we do the transmittance one, not the absorption one? All spectra we draw mostly absorptions, but in IR cases mostly we do the transmittance. Any reason, particular reason? Why we do transmittance? Not the absorptions. Have you ever asked about yourselves, like why? There should be some reason, isn't it? Why you do that? So when we talk about this transmittance, okay, that depends on how good you are making your sample, isn't it? When a light passes on some samples, what happens? Some light will be absorbed, some light will be transmitted, and some light goes where? It's a diffraction, isn't it? So when you are, that's why when you are given a sample, they are asked to make a very fine powder, isn't it? So that you reduce the diffraction light. Generally, when you have a particles which will diffract more, isn't it? When you have a particles, but when you have make it very nice fine powder, the diffraction will be reduced. That's your particle property of your light. So, based on your absorptions, some compound can absorb more, some compound can absorb less, but the transmittance light and the detector, they are kind of generated from a very less amount of light which will be transmitted that can detect. Because absorption means it has to be detected, so much of light will be absorbed, isn't it? So the detector which you are using, it can be detected very light, like very less amount of light which is coming out. So that means the efficiency of your IR spectra is going to be very high there. That's why the transmittance are plotted or transmittance are taken, not the absorption. Okay. So now this identification of particular bonds in the molecules, and then identification of a compound by direct comparison of the spectra, and how we are going to interpret it. It is the IR spectra are complex due to many different vibrations. That's okay. Yeah, I think we come to here. So till now, whatever we have learned, just we learned without seeing a spectra, just visualized in our brain, isn't it? Okay, a spectra which will look like that, because you are now in your, most of you are in your masters, isn't it? So that's why you know how your IR spectra look like. So this is your transmittance, and then it is plotted, and what will be your x-axis? That is going to be your frequency, and that is going to be in your wave number. And that's what I was talking about. Till 800 to 900, they are kind of for your fingerprint region. Why? Because the organic molecules with CC and CH bonds will have a peak around that 400 to 800 to 1000 centimeter inverse, which are going to be either vibration small, or there will be bending mode, there will be like different types of stretching, and they are going to be very complex spectra. That's why all the time that region we don't see, or we don't give any importance to that, because that's the thing where we call as your fingerprint region. So now we will go about how this IR spectra of a carbonyl compound will look like, and where the peak should be coming. It's mostly at 1700 to 1760 centimeter inverse, and then it is for your OH of alcohols, which will be around 3200, 3400 to 2600, and they are going to be broad. Why they are broad? Because they are going to be participated in your hydrogen bonding, isn't it? That's why your OH, NH, they are going to be broad, but the CH are not. Your CH signal comes around 3000. It's like 2900, 3000, okay? But they are going to be sharp. And when you have a NH and when you have OH, they are going to be broad. So, but if you keep that in mind, when you are deducing a structure, whether it's a CH or NH or OH, you can say, okay, if it is a broad, they are going to be those. And if it is a sharper one, then they are going to be your CH spectra. Okay, and this is for the carboxylic acid, because carboxylic acid will have your OH as well as your CO. That's why you get two types of signals. One is at around 1700, another one is around 3200, 3400. That is going to be your carboxylic acid. So that study material you have sent, or it will be done after the class? Okay. So that has actually both IR and NMR things also, and that you can give them. So there you will see some of the spectra, and it's in a very nicely built one. This is for your esters. Now here are some pictures of alkanes, means when you have a CH group and how it will look like. So if you see that this spectra which comes around this region, around 1200 to 1400, they are going to be bending modes, which is in your fingerprint region. But when you have see here, it's around 2900 to 3000 centimeter inverse, and they are going to be very nice sharper peak, not like a broad peak. Okay, so they are going to be your CH stretching frequency. By the way, when you have an alkane and when you have an arene, which CH you will see a higher spectrum than? Suppose you have an aromatic system and you have an aliphatic system. Okay, so which CH will be giving higher frequency IR? Aromatic one, isn't it? Why? Hybridization of your carbon, isn't it? That's simple. Because in your aromatic, all the carbons are your sp2, and in your alkane system, they are going to be sp3. So you see a typical spectra when you have an alkene with a conjugated system. Okay, so it's a conjugated alkenes. Now you see this alkenes with your symmetrical stretching and your asymmetrical stretching. So generally the alkenes CC double bond comes at around where? It's around 1600 to 1640. Okay, but as soon as you bring one conjugation, like another alkene, so what you will see, they are now not in a like a particular CC double bonded species, they are kind of an alene system it becomes, isn't it? So it's like a C, 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 all are going to be partial double bond characters. And you will see the stretching frequency drops down to 1590 centimeter inverse. From a 1640 to 1598 centimeter inverse it drops down because of that conjugation. So these are the like very highlight of your things what we have seen. If you have a OH or NH, you will get a signal like a broad one. Okay, like your alcohols. When you have an aldehyde or ketone, you are going to have a 1700. And when you have a CH, you are going to have a peak about like this, around 2900, 3000. And when you have a OH and CO stretching of your carboxylic acid, you have a two types of stretching frequency. So these are the highlighted portions which I have shown here in these slides. Now if you are given a compound which have these groups, I think by now you can tell them what are the functional groups you have. And if you are given a particular thing to tell that which will show a higher frequency and which will show a lower frequency, I think by now you can deduce them very nicely. I hope that you are in that stage now, isn't it? Or no? Huh? Some more practice. Okay. So till now what we have discussed, we discussed all mostly on your organic systems. Okay. Some of the aspect of your inorganic metal carbonyls also needs to be discussed, because when we are talking about catalysis, we cannot leave these transition metal carbonyl complexes as well, isn't it? Because transition metal carbonyl complexes are used in your transition metal catalysis. Like, can you name one example? A metal carbonyl, transition metal carbonyl, which is used in metal catalysis. CO2, CO8, isn't it? Cobalt carbonyl is used in where? Hydroformylations, isn't it? Or you have not read it? You read some and you forgot by now. So why we are trying to tell them? Because when a transition metal carbonyls coordinate to your organic molecules or some ligand, how their stretching frequency is going to be changed. And from here we can tell that, okay, that bond which is attached to a transition metal, whether it is an para or it is an ortho, or in which position it is attached. So IR can be a very good tool for that. So this is same thing which you will get it in your study materials, where the signal comes from the IR for the organic molecules. Now going back to here, metal carbonyls. Here are the few examples of metal carbonyls. Okay, like you have nickel, iron carbonyls, chromium, manganese, cobalt, osmium, iridium. Other than that, also some others are there, like molybdenum, tungsten. All the carbonyls are there. By the way, just being intrigued by my things, like if you see all these carbonyls, what are the oxidation states of these metals? All the metals are in zero oxidation states, isn't it? And what is the first? So their zero oxidation state means they are the lowest or low oxidation state. So to stabilize a low oxidation state molecule, you need this kind of ligands, isn't it? Which will accept the extra electrons on the metals. So these are called your pi accepting ligands. These are called your pi accepting ligands, because carbonyls have the pi star orbitals, where the electrons on the metals will go and to the pi star anti-bonding orbitals of the carbonyls. Other than this, they are not going to be stabilized. Okay. So I just throw questions to you guys. So in your, till now, whatever the things you learned, what is the first compound you learned with a very low oxidation state? The first compound you learned from your early school learning to till now, what is the first compound you learned transition metal having the lower oxidation state? Anyone will have some answer? That you have learned when you in your BSc maybe, but in your school days you learned that. 11 you learned learned this thing, isn't it? But before that also we learned that. Something you have heard about this ring test, Brown ring test. Huh? So what compound that was? That was of iron compound something, isn't it? With Fe, isn't it? And some nitro group used to be generated, NO. And what was the oxidation state of iron there? Anyone remember? In nitrous compound it was not +3. Then I will not have asked you. If you go back and see, it was -1. Iron was in -1 if you go back and check. So without knowing we learned that. But now we are coming and seeing that because nitrous compound was the NO+, and which is a very good pi accepting ligand. Without that, that compound was not forming. Okay? So we learned that, but we did not know that time. Having or to have a very low oxidation state, we need to have a ligand which can take the extra electron from the metal centers. Okay. So this is the thing I was telling why we study about this IR spectra of this, because of the some of the carbonyl compounds that used, like your rhodium carbonyl compounds, where it is used in your methanol to acetic acid processes. So this everyone knows CO molecular orbital theory, and this is a very simplified version, and you will see this, the HOMO is in the sigma, which is mostly on carbon, and the LUMO also on the carbon. So that's why oxygen being a very higher electronegative element in carbon monoxide, the attached comes from where? The ligand attaches through the carbon, not from the oxygen center. Carbon monoxide, generally ligand which has the higher electronegative element, they will attach to the metal. But carbon monoxide has a different scenario here, isn't it? It attaches through the carbon, not through oxygen. So why? If you see the molecular orbital, this electron on the highest molecular orbital, it is where it's situated near the carbon. And the accepting property of the carbon also, it is on the carbon. So that's why the carbon monoxides, it gives through carbon and it takes into the carbon oxygen, that pi star orbitals. Okay, so if you see this is your organic molecule, and now when you talk about this metal carbonyls, if you see this, now the stretching frequency increases where? It increases to 2000 to 2100 centimeter inverse. Okay, when a CO molecule is attached to an organic system, it is where? It is around 17 to 1800 centimeter inverse. But when it is attached to the metal center, where it is? It is around 2000. So why so? Any idea? See, it's something to do with bond strength, isn't it? Other than that, nothing else is there, because we have carbon, oxygen, so reduced mass option is gone. So it has to be something to do with your bond strength. So bond strength means in your carbonyl, generally you write C triple bond O. Isn't it? You write C triple bond O. So that means your carbon oxygen bond strength is going to be more in your metal carbonyls than in your organic molecules, because organic molecules it's C double bond O, we write it, because other two carbons attached to the other two groups in your organic system. Is it right or wrong till now? Or you are okay with that what I have told you? Huh? Not fine? Okay. Now this carbonyl, if you see, they can be of two types, isn't it? They can be bridged or it can be terminal. So when you have a bridging carbonyls, the stretching frequency will be increased or decreased? Obviously going to be decreased. Why? Because the carbon CO bond, it is taking electrons from where? From the both the metals. It taking electrons from the both metals. So when it takes electron from both the metals, that means their carbon oxygen bond strength is going to be reduced. That's why the stretching frequency of the carbon oxygen is going to be, in bridging, it will be lower. So why I got this, I will tell you here. Now when you are doing some reactions in your organic reactions with these carbonyls, when it loses or when it accepts electron, that means the metal is changing to either positive, your cationic, or a negative anionic form. And by doing the IR spectrum, you can say whether the metal is in your positive or your cationic species, or it's going to be an anionic species. Because if you have an anionic species on the metal center, that anion is going to be given to where? To the ligand. Which is the ligand? Your carbonyl ligands. And in that case, the stretching frequency of the carbon is going to be, carbonyl will be reduced. So if you have a particular metal with a positive charge and a particular metal with a negative charge, which you have generated during the reaction process, and if you run the IR of that, you will say, oh, it's a cationic species or it's an anionic species. Okay, so that's why we should know some amount of this also. That's why I brought this to you. And this is a classic, some examples of the metal carbonyls when you have a extra ligand. That means you are generating or giving more electrons on the metal center, and that electrons is going to be given to the carbonyls. And that's how the stretching frequency is going to be altered. So because when you do a substitution reactions on the metal center, these are the things are going to be taken into account. So this is more or less of your, so this is a real example of a paper recently described, the CO2, carbon dioxide, how it bind to the metal center. So they have done the IR and they have shown that the CO2 has bound in some different fashion which was not known earlier. So they run the IR and they saw that this CO carboxylate moiety, which is at 1628, because CO2 would have gone from the oxygen side, but it is given from oxygen carbon, so it's like a bridge between carbon and oxygen. So that's how the CO stretching frequency changed. And by running an NMR, they could show that, okay, it's possible to see whether the carbon dioxide attached to the metal in which fashion. So these are the tool, like IR is a tool, people can use it for different aspects, not only your organic molecules, but while doing a catalysis process, also it is possible to understand. So till now, what are things we learned? So the last point, if you see, it was the first slide, isn't it? If you see the last point, it was the first slide, isn't it? How does the transition metal and the main group catalysis are different? And I hope that at least you keep that in mind when you work on something. And we learned IR, some of the basis and how does it work, and factors that affect the IR spectra and how important it is to study the transition metal carbonyl complexes, and some interpretation of the few IR spectrum, which I will also supply to you, which you can check how you can interpret them. Okay, we can have some 5 minutes and then we can go into your NMR. Just 5 minutes, then we will go to your NMR, next topic, okay? Okay. So till now we were at IR with the 2 letters, isn't it? Now we're going to NMR, so 3 letters, isn't it? So that means these instruments or this technique is going to be more advanced than IR, whatever you learned. Huh? So you are in first year or second year MScs? Most of you are second year MSc. So that means you have studied some aspect or some portion of your NMR as well, isn't it? Why I start with this NMR first today, proton NMR, and then because tomorrow mostly we will be talking about either phosphorus, fluorine or boron NMRs. Okay? So NMR is a technique like your IR techniques, where in your IR what we were doing, we were changing what, or we are giving energy where, to the bond of the molecules. And here what we will do, we are giving energy where, we are going to give the energy to flip the spin of the nucleus. And what energy is required for that? It's a radio frequency. Okay? It's a very minimum energy, because radio frequency comes at the most right of the your energy series. By the way, most of you use your microwave, isn't it? And what you do in your microwave actually? You make your food hot up, isn't it? Heat it up. So how it works? Huh? Water in the food will get heated up. How? Rotation, because the microwave will be given to where, and it has to have, if you have noticed that when you make or heat up a food, it will heat up in the middle first. If you break your food apart, you will see the side is fine, it's not so hot, but in the middle it's too hot. So that means the water molecule, where it is more abundant, it's going to heat it up more there. So the side of the molecule, side of the food does not have so much of water because it may be evaporated. So in the middle of your food you have more water, which is going to heat it up more, because it's going to be, water molecule is going to be heated up. So similarly in NMR, what we are going to do, this is the radio frequency. Okay? In IA we were talking about the infrared. Now in here we are going to talk about the radio frequency. So which will be transitioning or giving the energy to more like a nuclear spin transition. Nice there. Thank you. So what happens here? Like when you have a nucleus with a nuclear spin, okay, that means a nuclear will be positively charged and it will have some kind of a spin. What spin? Like you have electron which will have a spin, isn't it? Either plus spin like a upward or minus spin downward. So similarly, when you have a nucleus with a, it will behave like a magnet. Okay, how? So when you have a nucleus with a spin of half, let's say, and then how many energy states it can make? It can make 2 energy states if you apply an external magnetic field. Either it can be with a similar to the parallel to the magnetic field, or it's an anti-parallel to the magnetic field. So based on that, what you are doing, you are generating 2 different energy states. Now the nuclear spin or nucleus from one energy state, it can go to the other energy state by taking that external radio frequency. Okay, so what you need here, you need an external magnet and you need a source of radio frequency. So these two things are required for the NMR. Now you can say that, so then how we will see a spectra? Because to see a spectra, you need to have a transition first. And then once the transition happens, that means the number of nucleus in your lower energy state and higher energy state, if it is same, that means what? They are in your equilibrium. That time you will not see any spectra, isn't it? Because when they are in equilibrium, there you are not going to see any spectra because there is no nucleus coming down or no nucleus is going up to. That means there is no energy, kind of an energy interaction is happening with the nuclei. So when a sample at equilibrium takes up the radiation, then what happens? It goes to the excited state and the spectra we see that. So you will see that in this slide, you see this, there are different types of spectroscopy we have talked about. One is UV visible, IR, and then the NMR. And these spectroscopic techniques are mutually complementary. You see this line. These three spectroscopy are mutually complementary. Means if you know that and if you know this, then you can conclude something about the structure of a molecule. So as a one entity, it is very difficult to tell. As in one entity, it is very difficult to say that. Okay, now just bring us to the history of NMR spectroscopy, and you see this, just the phenomena was discovered simultaneously by two groups. One is Purcell and Torrey at Harvard, and another one is Parafilm Block at Stanford. Okay, so this Waters is a company actually, which is later on changed into, they have made a company on this name. This was the case in 1945. And what is the year 1945? One more significant thing happened. The Second World War finishes, isn't it? That is in 1945. And in 1950, the first NMR spectra of ethanol was recorded by Arnold and Packard. Okay, so this is the first NMR spectra of ethanol. Now in 1952, the first Nobel Prize in Physics was given to that Block and Purcell for this NMR. And 1991, the second Nobel Prize in NMR for chemistry. And 2002, the third Nobel Prize in NMR chemistry was awarded for the determination of the structure of the biomolecules. And 2003, again, the fourth one in medicine for the MRI. Okay, so this MRI also is on your nuclear spin. And nowadays, I think something happens, do an MRI test, isn't it? Although a little bit costly till now, but people are now getting afforded. So these are the history of your NMR spectroscopy. So if you see, already 4 Nobel Prizes are already done in this technique. So how important this technique was. So if you see this, this is the randomly oriented nuclear spin of equal energy in the absence of any magnetic field. So if you have the idea of electron spin, it is more or less same thing. Now when you have nuclear spin of I equals to half, that means there are two possibilities according to this 2I plus 1 rule. So that means it can have a orientation spin according to the applied magnetic field and orientation of the spin to the, what is this called? It is like a anti to the applied magnetic field. So suppose you have total 6 nuclei. If you look at here, if you have 6 nuclei spin and they are in the 2 different states, plus half and minus half. Now by taking the electromagnetic radiation, it can flip from one this to that one. So the nuclear spin flips, isn't it? So that flipping, that energy, whatever it took from the radio frequency, now when you come back from there to here again by flipping, we will see that NMR. Okay, so how much energy it is taken to resonate and then flip from one energy state to another energy state, that much energy will be now released when it come back again, and that will be your NMR spectra will be plotted or recorded. Now you think of a situation where instead of these two, you have more levels. You have more levels. That means an electron can go from one lower energy state to some other energy levels as well, which can be correlated to your UV spectra if you think about. So if you think about a UV spectra of a transition metals, okay, so they will have a low-lying similar energy, isn't it? And when you have a low-lying similar energy from your lower energy state, the electron can go to this or that. An electron does not know where to go. So in that scenario, what you see, a spectra you see not very sharp, rather than you see a very broad spectra. Or you see sometimes a hump in your spectra. If you remember, you see a hump in your spectra. Why? Because the energy between two electronic states, they are more or less same. So the lower electronic states of your electron, they cannot differentiate where to go. So that's how you see a broad spectra or hump in your spectra. Similarly, you make a situation where the energy states are different. That means electron can go to any other state. So that means in those cases, your NMR spectra are going to be what? Not very sharp. They are going to be a broader spectra. Okay, so when this will arise, when you have I value more than half. So if you have a half I value, then only you have only 2 energy state. But if you have a I value more than half, like 3 by 2 or 1 or more than like 5 by 2, sometimes you will see some of the nuclear spin has 5 by 2 as well. So then what you are generating several energy states. Now that electron does not know where to go, or that nuclear spin does not know where to go. Okay, so in that situation, we will see the spectra are more or less going to be broad spectra. So when we talk about those kind of thing, mostly your boron NMR going to be, you will see most of the boron NMR are going to be broad. Why? Because the I value for boron is 3 by 2. That means instead of generating 2 energy state, 3 by 2 means you are going to generate how many? 4 energy states, which is the notation of your quadrupolar movement. Okay, so that some aspect we will talk about tomorrow, but this is the basis of it, why we see some of the spectra broad, like your proton NH spectra, if you think about, okay, and OH spectra, they are going to be broad spectra also. Why? Not that they are going to be exchanged with your solvent, but also they are not in the same state, isn't it? They are not going to be in the same state. Now, which brings me to here, you know this uncertainty principle. What is that? What is uncertainty principle? Tell me, what is that? Position and momentum, isn't it? They are not going to be, at a time we cannot differentiate that. So that same thing was applied here as well. That is your energy and time, or time and displacement. If you think about time and displacement, suppose you have to define energy. So your nucleus knows I have to go from this to that, and then it comes back. So you have a particular energy difference. Now you have made so many energy states. So your nucleus does not know where to go. Now what will happen? So you are not defining the time. So when you are not defining a time, that means your NMR machine will see so many, like an average from here to here, this much. Okay? So your time, that is called relaxation time. Okay? So when your relaxation time is so less, your NMR machine cannot determine where exactly I am seeing that nucleus. So that is why you are going to see your broad like a spectra, like an average spectra. Is it understood now? So now if anyone asks you why you see a broad spectra, I think you should not say that I don't know. Okay? Okay, the spinning of positively charged particle produces spin angular momentum and magnetic moment and electronic quadrupole moment. That's what we were talking about. Okay. Now this angular momentum of spinning nucleus, it has I value and it can have three different rules which we study generally. It's your odd and even number of mass and atomic number. Okay. So when you have nuclei with odd mass number and odd or even proton numbers, the integral, the I value is going to be half integrals, either 1 by 2, 3 by 2, 5 by 2, 7 by 2, like that. Okay. So what is the main component here? The odd number will be, the mass will be odd. Okay. And if mass is odd, don't see if here down whatever it is. Atomic number will be odd or even, it is going to be 1 by 2, 3 by 2, 4 by 2, 5 by 2, like that. And when we are talking about nuclei with even mass number and odd number of protons, so that means the integral spin will be going to be, I value is going to be 1, 2, 3, like that. And when you have both mass and atomic numbers are going to be same, then you don't have I value, it's going to be 0. That means that nucleus is going to be NMR inactive nucleus when your mass and atomic numbers are going to be same, like your both are even number. So I know that you have learned, you have studied these things, mass number and atomic number, but I'm sure that you have not studied why you see that broad spectra, isn't it? So keep that in mind, definitely it will help you. So now we will see some nuclear properties of important nuclei with I value. So if you see this nucleus 1H, like proton NMR, which is the first thing we do, and you have the spin value is 1 by 2, and the abundance of that, what it is, 99.9%. That means why we do proton NMR first? This is an example, classic example, because it has only I value 1 by 2. That means only 2 energy states, and the abundance is more than 99%. That means if you have a very minute amount of your sample, in that 99% you will be have a proton there. You can, NMR can see that. Okay, these are the proton nuclei I can see. Because your NMR has to see the nuclei, isn't it? If you want to do the carbon, then NMR has to see the carbon nuclei. And the carbon abundance is very, very low. because carbon 12 carbon is NMR inactive. So it has to have a 13 carbon which is NMR active, but the percentage or abundance is very low there. Now you see about boron NMR. You see this, the I value is 3 by 2 and the natural abundance is more than 80%, it's like 81%. So that's why boron NMR can be done, but only thing the 3 by 2 things, which you will get a broad spectra. So you have to be very, very patient to see the spectra. It's not going to be like a proton NMR, just go run within 2 minutes you get it. So you need some time. Carbon 12, I value 0, carbon 13, only 0.1% you see that, natural abundance. Although the I value is 1 by 2, but the natural abundance is going to be less. And then you have 14N, 15N, fluorine, silicon and phosphorus. You see this fluorine and phosphorus, they are 100% abundance. So they are kind of more or less kind of a proton NMR because I value is also 1 by 2. So phosphorus and fluorine NMR, they also behave like your proton NMR because the I value is 1 by 2 and the abundance is 100%. So there is no problem in getting the NMR in very quick time. So similarly, there are some other element which is 100% abundance. There are I think 5 or 6 element. If we take proton as 100%, as it is more than 99%, then there are 5 elements which has that 100% abundance which are NMR active. Anyone knows about that? No? So I'll tell one, another one you find it out. Okay? One is rhodium. Okay, rhodium NMR when you do, that is also 100% abundance. And the other one you find it out, what is that? Okay. So this is the thing which you have seen earlier, but here what we see here, the energy which is required from one state to another state, that is delta E, which is related to your external magnetic field, which is H0, and there is another one which is called mu, and this is related to your these things. One gamma came, isn't it here? And what is that gamma here? It is a proportionality constant and which is named as a gyromagnetic ratio. That means each nuclei will have a value, that is your gyromagnetic ratio, which is different. Each nuclei will have a gamma value different. Okay? In that it is going to be differentiated, which how much energy is required. Now you think about one thing. When you record an NMR, okay, what we do? We can do two way. I think in the next slide, if it is there, I will show you. Yeah, this one. You see this? Two ways of doing NMR experiment. One, you can change the magnetic field. Suppose you are giving a sample and then you are changing the magnetic field. Okay, that is one way of doing. Another, you are giving a sample and then you are changing the frequency. So which one is easy? Frequency means your radio frequency. Okay, because you need two things here in NMR. In IR you needed only one, only the IR source. But here you need two things. One is your external magnetic field, which will make the nucleus as a like your magnet, and second, you need a radio frequency now to jump or to make that nucleus jump from one energy state to another energy state. So what you are going to do here? Are you going to change the magnetic field or you are going to change the radio frequency? Which is more easier to do? changing radio frequency, isn't it? Because if you are given a source, you can tune that source. But external magnetic field, you cannot do that. Because every time that you are taking out and putting a new magnetic field, which is very, very difficult to do that. Or you need to change the temperature differently to change the magnetic field. Suppose at that temperature, it will give this magnetic field, and after changing the temperature, it will generate different magnetic field, which is very, very lengthy and very, very cost effective, not cost effective process. So what is the cost effective process? It is your frequency. So you have a general source. Now you can tune the frequency according to your magnetic, like what magnetic nucleus you want to see that. If you want to see the proton, you give this frequency. If you want to see the carbon, you give another frequency. Or if you want to see the boron, you give some other frequency. So you are changing the frequency, not the magnetic field. Quadrupolar movement. Yeah. So this is the magnetic or NMR spectrometer work. It is working like that. So you have recorded the NMR, any one of you? You have seen NMR spectra, some of you. So what you are doing, you are making your sample in an NMR tube, okay, and then you are going to the machine, and then you give that or just place the magnet sample into the machine, and it takes down where the magnet is, okay. You will see very long like this, isn't it? But the magnet will be on the down. So the magnet, your NMR sample will go down, and it will rotate there, okay. And then once the NMR is done, there will be positive air pressure which will bring your NMR sample from down to up to take it out, okay. And that pressure should be your nitrogen mostly. And if you are not having that pressure, then what will happen? Your NMR sample will go and down and stuck there, okay. And if it is stuck, what you have to do? You have to open up everything, taking out things out. So when you are making a sample, should be careful about your NMR tube. It's not broken, it has no crack, because little bit of broken things, it can give a very, very like 1 day process to clean up everything, okay, and it will hamper everyone. And that is one thing. Second, how you prepare an NMR sample actually. Can you fill your NMR solvent with everything? It is not possible to do it. First of all, the NMR solvent are costly, okay. So you cannot fill the bottle of NMR in NMR tube. So, and there is a minimum amount is required to run your sample. If it is more than that, the NMR machine cannot see that level, because if it is less than that, the NMR machine will not detect that you have the sample. So there is a mark given, you have to give this much of sample or this much of solution to run your NMR sample. Okay, so the sample tube is going to be placed on top, then it goes down and it will be rotating, and the magnetic controller will be there, and then the radio frequency is going to see this. With the detector, we are going to see the NMR spectra. So that's how the NMR spectrometer is aligned with. So how will NMR graph look like? It's more or less like this, isn't it? So this is your increasing magnetic field strength, and then you have a less shielded proton which will be coming to your left hand side, and highly shielded protons will be your right hand side. So what is this shielding things? What is the shielding things? That means shielding of what? Or shielding by what? Shielding by what? Like we talk about electron shielded, isn't it? Like d orbitals are so but shielded, f orbital shielded. What shielding is here? Here also same thing. We are talking about the electronics only. So when you are seeing a magnet, the nucleus, that means it is kind of your spin, isn't it? So similarly, if you have a free electrons near to that nucleus, that means that electrons are going to be as your magnet, like your magnet, isn't it? Because they also have a spin. And you cannot just deny that I will not talk about that, or I will not see that electrons are there. I will just only see the protons or the nucleus, which is not going to be true. So what has to be done? If you have or talking about a proton which has more electron density around it, that means it is going to be more shielded, and that NMR will come to your right hand side of that. And if you have a less electron density around that proton or around the nucleus, then you will have a less shielding things. Now if you have studied NMR, now try to make that or think that things. Like if you think about an OH proton or an CHO protons, isn't it, aldehyde protons, where it comes more or less your left hand side, isn't it? Because your CO groups are going to taking the electrons from that side because they are more electron withdrawn nature. So the electron density around the proton is not so much. So that is why it is going to precise on what? On your left hand side. But if you talk about a hydride like a BH4 minus, so the proton is not here a proton, it's a hydride nature. That means your electron density around the proton is hydrogen is too much. That is why instead of coming at your left hand side, now you will see them coming on your right hand side of your spectra. So which proton will be shielded and which proton will not be shielded, if you need to tell about it, just see around what it has. And from there 99% cases you can explain them. Maybe one or two will be exception, there will be ring current and blah blah things, but that you need to learn it or you will see that. Now NMR signals. So how many signals we will see? Okay. So first of all, how many different types of nuclei are there? We are talking about that many types of NMR signals we will see. Suppose there are 3 types of protons, we will see 3 NMR signals. If there are only one type of proton, then only we will see only one NMR signals. And the shielded and deshielded I told about, and how the intensity of the signals will look like. That means how many numbers of protons are there, based on that you will have the intensity of the NMR signals. If you have more number of protons, you are going to see the intensity more. If it is less number of protons, it is less. And there is another pattern term comes in, that is splitting of the signals. So how it is going to be splitted? Okay, so the splitting of the protons depends on what? The nearby protons or nearby nuclei. So how they are going to affect that particular protons, by that we will be seeing the splitting of the signals. Like if you see the intensity of the signals, if you see this, like you have 2 types of protons, isn't it? One is this CH3 and another one is this 3CH3. Okay, so you are going to see them indifferently. So there you will have 9 protons and you will have 3 protons here. So you are going to see them in a different manner. Like you will see this spectra here, you have how many types of signals? 1, 2 and 3. Everyone understood? So you will have 3 types of signals for 3 types of, you have 1 and then 2 and 3, okay? So now, if you are integrating these 3 signals, you see how they are getting, it is coming 3.8, 2.9 and 8.8. The integration of the signals says that. So 3.8, 2.9 and 8.8. Now if you make them ratio, either it is coming like 3:1:1.3, or if you multiply, it is coming 3.9. So generally, if you are seeing that a proton NMR with an integration coming more than 0.5 or 0.6, we take as a whole number. It's like either it is going to be 2. So if it is a 1.7 or 1.6, we take it is a 1. It's into a 2. If it is 3.8, we consider it as a 4 number of protons because of these things. Now you see this. This is the molecular formula of C11H16, and you have a 16 hydrogens, but total number it is 15.5 if you plus them, 3.8, 2.9 and 8.8. So it's coming what? 15.5 units. So for 16 protons, total number of units is 15.5. So the per proton has how much contribution? 1.03. Now you multiply them, you get the number 4:3:9. So you get that. So generally this is the complicated way to tell that, but in a simple way, if you are getting a signal which is suppose 1.7, you will consider that as a 2, or if you are getting 1.3, you will consider it is a 1. So that's how it is simple. Because we are the first time how to calculate it. So that is the way of doing it. Now this is an example of keto-enol problem, isn't it? You know what is keto-enol? So there are the 2 isomers of a molecule where this CH2 is an active CH2 which can go to a 6-membered ring by the hydrogen coming here. So you get a keto-enol formalism. Now in a molecule, how much percentage of keto compounds are there and how much percentage of enol compounds are there, that we can differentiate from where? From the proton NMR spectra. Because of this CH protons or that OH protons, if you are considering or if you are integrating this versus this, okay, so you have for this molecule you have only one alkenic proton here, but this is your alkane proton, isn't it? So you will have different position that proton comes in, and based on that you will see how much ratio of your keto form is there, how much ratio of your enol form is there. You can differentiate from the NMR spectroscopy. So this is the shielding and deshielding of a proton, what we have discussed. Now if you are talking about this like a ring current and your precision and everything, what I have told, it is more or less in the same thing. Okay, if you are talking about this thing, you see this, how many types of protons are there? 3 types of protons are there. Now you have this CH3, CH2 and H, isn't it? And which one is going to come as a deshielded one? OH proton is going to come as a deshielded one because it is connected to your oxygen, which is electron withdrawing in nature. So that means the electron density around that proton is less. Okay. Now which is connected to the next oxygen like a hydrocarbon, so that will be little better. And the CH3 group which is away from oxygen, that is to come into your right hand side. Okay. So is that understood or not? So why it is so? Because of the same thing, the applied magnetic field and electron density around that proton what NMR machine is seeing. Now you need a reference standard in NMR. Okay. So why you need? Because for what the NMR machine will tell this proton is based on what? Because you need a relativity things, isn't it? So that's why you need a reference, and the reference should have this chemically inert, non-reactive, and it should have a single sharp line, and it will be unique in line position. All these things should be there for having a reference in the NMR standard. Okay. So these are the different solvents people use for the NMR, either CDCl3, D6-benzene, DMSO, all these things, and we need a deuterated solvents. Otherwise, your NMR machine cannot differentiate whether it's a proton or deuterium, isn't it? So it will give only the protons. And you will have chemical equivalency. I will now go to some of the signals or yeah. So this is a thing like how the signal will look like, chemical shifts. Yeah. So if you see about one NMR is going to be splitted by the other, like one proton is going to be splitted by the other proton or other nucleus. So how many numbers or lines you will get? You all know that is going to be again 2Ni plus 1, okay, that is the multiplicity. So the n depends on the nearby one. Suppose you are seeing this proton, so you have to see this proton, how many protons you have. So that many protons are going to be coupled with this to give you the number of lines it is. So if you have a 3 protons here, then you are going to get how many? So it's a 4 lines, it will be a quartet, okay. And if you have 2, it will be triplet and so and so. Although it is not very simple, just simple, that's the way I told you, sometimes it is complex as well. Like if you see this, like you have the styrene and you have 3 different protons and you are getting 3 different types of signals, isn't it? Although we should get doublet or singlet or triplet based on that, but we are getting a different types of things. So why we are seeing that? That depends on the coupling constant. Okay, if your protons are similar protons which are going to couple with the other one, then the coupling constant are very, very small. That means the line between the splitting between the 2 lines are not going to be so simple. So they are going to be merged together. And instead of getting a very nice better line, you will get kind of a merged things, which is the name like your AB or AB type or AX type coupling constants. So if there are more examples which you will, and this slide maybe you can give them once this is done, this slide also. Okay, I will share it with you. You can forward them. There are some other things which they need to learn it, which I have not discussed some other things. Like I will just give this example one and then we can see these things. Like if you have a coupling constant which are very, very similar, then how you are going to see, and the coupling constant is very different, then how the NMR lines you are going to see. So if you see the coupling constant or this value is very, very like it's more than the coupling constant, then you are going to see that line very, very separated. But if they are more or less similar, then you see that line, whatever you are seeing here away, it is coming closer together. And when it is less than that, then it looks like kind of a quartet. Instead of getting 2 different signals, you are getting kind of a quartet. So this is all depends on what? The coupling constant of the 2 protons which are similar or equivalent in nature, they are going to couple with the other protons. So that will define how the coupling constant will look like. So this is the equations which you can see, and the very bad way of converting things it is actually. And how the equivalency or non-equivalency due to some restricted rotation happens. If you see this is the fluorine NMR which we will discuss tomorrow. Like if you have two different fluorine, Fa and Fv, due to the what is this called, non-equivalency of restricted rotations, they are going to be either this or that, and they are going to be coupled with each other to get you the different type of spectra. So today till now whatever we have learned from your IR and then some aspect of your NMR, mostly on the proton aspect, okay, and how the splitting will look like, how the NMR is going to help us to differentiate between an aromatic or an aliphatic or an shielded or deshielded protons, and then this will help us in tomorrow to see some of the examples with different heteronuclear NMRs. So I hope that in today's class you learned some of the aspect of your NMR and IR, and if you are given a sample and given a spectra, and you can tell that this spectra is for what type of sample. Okay, so at the end of the class you will be able to differentiate, or you will be able to tell that okay, I have this kind of a spectra, means I have this kind of a molecule, this structure of the molecule will look like that. Okay, so here I will stop and I will leave you for some time for before your next class happens. So you can stop that maybe.
I don't think you guys have any idea what do we do exactly, the computational chemist. Any idea? No idea, right? Now, you all have studied thermodynamics at least, right? Why you study thermodynamics? Why it is important? I mean, that is important. Do you think that course is important, right? You study in BSc, right? Bachelor's. Masters maybe they have here. In some places they have in masters also. So any idea why we study, in fact, any course, right? Like any course you take, right? Let's say thermodynamics. Why you study thermodynamics?
Some things like rate of reactions and all.
Rate of reaction, right? Can you apply in your reactions, chemical reactions you do in the labs, especially the organic chemist, do PhD students?
I'm not a PhD student.
I'm asking personally the organic. I mean them. Okay. Can you apply? So thermodynamics, right? I'm not talking. There are so many types of thermodynamics. There is a thermodynamics you study. Then you have a statistical thermodynamics. I don't think you have taken that course. But basically similar things. And then there is a quantum aspect of thermodynamics. So we have these three courses, right? And like I said, any courses you take, I mean, they must have some importance, right? Like you doing PhDs, whoever doing PhD. So no idea, right? You have any idea? Let's take give me reaction, any reaction, no choice. I'll write it down and then I'll tell you why it is important or all. Why thermodynamics is important. Then I'll talk about the computational part. Yes? Understand very simple things. Any reaction, name it. Huh? Okay, if you don't want to say, I'm writing one reaction. Okay, suppose ethylene C2H4 plus whatever, half O2, right? This reaction, epoxide kind of reaction, right? These are organic reactions. And you all have studied thermodynamics. Tell me what is important and how it is important for this particular reaction, thermodynamics. Anybody? So I'll give you some hints, right? One is, delta G, free energy. You have been taught in thermodynamics, right? Shall I use this board? Maybe this is better. So this reaction half auto, right? This is a reaction. Now you all know, I have studied thermodynamics, right? See, even if you do organic synthesis, you must understand, these are the very basic things I am going to talk. So tell me, what is the relation with delta G? What is delta G? Gives free energy, right? Changing reaction free energy. And you studied that, right? So delta G, there is an equation called delta G equal to delta H minus T delta S, right? You know that, this, right? I will go back to computational chemistry. Let's understand this. So any reaction you pick, you have reactant and product, right? These are your reactant, this, and this is your product, right? And you know the delta G has to be negative, the reaction. Then it is an exothermic reaction that you have been taught, right? And it is an endothermic reaction, the reaction will happen or not? Reaction will happen?
Yes.
How many of you say reaction will happen, how many of you say no, reaction will not happen? Then why it is why exothermic and endothermic, why it is important? Huh? Del H. I'll come back to del H and all. So let's talk about delta G. Okay, there are two parts. One is delta G, and then there is this side two part, you delta H, that is enthalpy, and delta S, that is entropy. Right? Now I'll tell you why these three are important. Let's talk about delta G first. If delta G is negative, then it is spontaneous. So suppose I have to study this reaction computationally, okay? Then I need to check whether delta G is negative or not. Right? If delta G is negative, then I can say the reaction is spontaneous. Delta G positive, reaction, that's what he is saying. Even in those cases, reaction happens, but not spontaneous. Like the moment you see tea outside, you will go hurriedly, right? That's a spontaneous, right? One result, everyone will go, right? So that means the reaction will happen, but does it happen so spontaneously? How many of you know this graphite to diamond? Graphite you heard, right? Diamond? Yes. Some of you like diamond, right? No? These boys, they do like, I guess. So, you know what is the delta G of the reaction? Graphite, the pencil you use, that is a graphite. And the diamond, I don't need to talk much, right? That is also carbon. Same, nothing. Only carbon element. And the delta G is close to negative. Almost zero. Or little negative. There are a lot of controversies, but it's not delta G is huge. But the reaction is very, very difficult. You know that how they synthesize diamond, right? It's a lot of temperature and pressure. So basically what I am saying is delta G negative is important, but that doesn't mean delta G negative we can it's spontaneous reaction. Delta G positive, if suppose delta G positive 100 kilocalorie, you can say no, the reaction will not happen, and that is true. If delta G is 10 kilocalorie, 15 kilocalorie, yes, the reaction will happen. And that's why you add temperature or pressure in your reaction or something, right? You add some solvent and all. Can you tell me what does temperature do? I mean, what temperature does in your reaction? So I have this ethylene, oxygen, I need this epoxide. How temperature helps here? You have to read in thermodynamics. I'm not saying anything new. There is one more term that is called kinetics, right? This is delta G. Kinetics is the barrier. That also you have studied. So there are two parameters. One is rate constant, K, okay? So this is a kinetic parameter. One is a thermodynamic parameter. Delta G is thermodynamics. Rate constant is a kinetics. Now which is more important? Both are important. Both are equally important. How many of you say both are equally? I mean, equally important? Then let me go back to diamond and graphite. Delta G says the reaction will happen easily. But does it happen? So what is important? It's not depending on the reactions. I can go back some other examples. It's not. It is kinetics that is the most important of all, not the delta G. So if you can calculate the activation barrier, in some experiments, these people, they can do some experiments. If you do photocatalysis, their kinetics is different. They're not like thermochemical reactions. I can talk about that also separately. But there are different types of reaction: thermochemical, photochemical, electrochemical, right? Let's talk about thermochemical. Thermochemical means temperature dependent. Okay? So I'm not talking about photocatalysis. These people do photocatalysis. I'm not talking about that. Photocatalysis, this delta G equal to delta, the reaction equation is same, but the kinetics, they're different. Because in that case, your kinetics is because of your electron. So it's an electrochemical, like electrochemical reaction, photochemical reaction, because of the electron energy. Here they have molecular energy. They are different. So thermochemical and photochemical, that's why kinetics is very, very important. When it comes to kinetics, they're different. They use the same concept, transition state model and all, but basically their electron energy, in this case, molecular energy is important. In that case, electron energy is very important, right? And now electron can be very fast, right? They like how fast electron can move, right? You know, electron kinetics or electron dynamics. Electron can move like at the speed of light, close to the speed of light, but your molecule cannot, right? Now going back, temperature and pressure, what exactly they do? I said kinetics. Kinetics, let's say kinetic energy. You know kinetic energy, right? What is kinetic energy? How many of you know kinetic energy? How many of you know total energy of the system? See, this delta G is actually energy, right? It's a total energy of the system. Let's say total energy of this system. And there are two terms. One is called kinetic energy. Kinetic is nothing, just molecule moving fast. Movement of the, so if you add temperature, what exactly happens? Your kinetic energy, they increase. So basically when you heat up your reaction, then you see product, right? You see earlier, you see the product formation earlier. That's not because of the thermal energy, no. Thermal energy is very little. Thermal energy is kT. K is the gas constant, I don't know, some of you know, and temperature. That energy is nothing. So when you add temperature in a reaction, the reaction does happen not because of thermal energy. It happens because of the kinetic energy. The molecules, they move faster and faster. Those molecules are there, like when they move faster and faster, they collide. And when they collide, then the reaction happens faster. Not because of the thermal energy. Don't get it wrong. kT is hardly 2 kilocalorie. whatever temperature you cannot achieve, you cannot go 1000 Kelvin, right? So whatever temperature you guys do, maybe maximum 100 degree, right? Thermal energy is nothing. So that is true for even pressure. If you add pressure, that means molecules are moving faster and faster because they are under pressure. Okay? So because of that collision energy, the reaction happens faster and faster. So that means delta G and rate of constant kinetics, thermodynamics and kinetics, both are important for this reaction. Now I said kinetics is more important because it has to cross the barrier, right? You all have seen that, right? So basically you can have a, maybe I'll delete this part, right? So the equation is delta G equal to delta H minus T delta S. Now this is energy, this is energy, this is energy, everything is energy, right? Energy of what? I have a molecule ethylene, right? Suppose C2H4. I have oxygen energy, and then I have this, right? Energy of what? Energy of the molecule, right? So molecular energy of this CTH4. So you calculate energy of this, you calculate energy of half O2, you calculate energy, and you see the energy difference. If the energy difference is negative, then the reaction is spontaneous. You can say, okay, this reaction is possible. So now how do you calculate the energy? That's where the computational quantum mechanics comes. Because you cannot calculate the energy of the system. Right? Now, before I move to how you calculate energy, what is in C2H4? Let me tell you in this reaction. Like this reaction, how many molecules are there? How many molecules we are talking here? One molecule? How many? Two? Three? Are you talking about three molecules? Please, what is the number? You don't agree, right? Tell me what is the number. I agree with you. That's the Avogadro number. So it is not of one molecule. It is one more than Avogadro number. So it depends on solution, how much solution you are taking. If you are taking 1 molar solution per reaction, per gas, right? This is Avogadro number of molecule. So it is not, we are not talking about one reaction. Basically, 10 to the power 23 number of molecules reacting with 10 to the power 23 number of half O2, maybe half of that, right? Giving 10 to the power 23 number of product. Don't think it is one molecule. Okay? Depending on the number of solution, but that is the concentration. So now, can we calculate to 10 to the power 23 energy of the 10 to the power 23 molecule? No. We cannot do that. So basically we will do for one molecule and then we will multiply by 10 to the, or whatever. Basically it is the average, right? Now in chemistry, I hope you all are chemists, right? In chemistry, what is most important? Well, for you guys can tell what is most important. Feasibility of the reaction, right? But I did chemistry, not organic chemistry. I don't do reactions, frankly speaking. Okay. So in chemistry, suppose you BSc chemistry, right? What is most important? What is the most important thing you think about chemistry? Huh? Quantity. Quantity of what? Product. That's fine, I have no problem with that. That's true also. Quantity of the product, maybe product selectivity and all, they're more important. Now, let me go back. So, it is product. The product is of what? It's the element, right? When you study chemistry in 10th or 12th standard, not even 12th, I think 7th or 8th standard, right? You have a periodic table, right? I don't know which standard, but do you have a periodic table, right? So how many of you really thought about product that time? It's element, right? And then what else? Element is, what do you have in elements? Elements composed of? Elements composed of, elements itself atom. It's not molecule, okay? So where atoms composed of? Electrons. So what is most important in chemistry? Do you agree? It's about charge transfer, right? Electron donation, accept. Nothing else. You accept, you want to study in BSc or whatever. It is almost, whether it will give electron or take electron. What else you, it's all about electron. If you are adding 1 electron, you are helium 2 electron, right? So basically 2 electron or 2 proton. Now, when I am talking electron, see in chemistry it is more about charge transfer, right? So basically, if I have to calculate energy of a molecule, if the energy of the electron is important or not. I am going back to your energy, right? So basically it is the electron energy. The electron in carbon and the electron in hydrogen or oxygen, their energy same or different? That means total energy of the system will be different, right? 5 electron, 6 electron in carbon or 8 electron in oxygen. One is number of electrons are different and second the So basically if I have to calculate delta G or energy of this system, that means I need to calculate the energy of the electron in that system. And that's quantum mechanics. I don't know how many of you know, if you studied quantum mechanics a bit, there is an equation called, that's computational chemistry, not quantum mechanics. So there is an equation called H psi equal to E psi. E is the energy. The energy you see there, they are same. So this equation, this guy Schrodinger, he proposed this maybe in 1920s, maybe 100 years back. And he proposed without anything, without any experimental. He said, you calculate the energy of the electron. Basically, you can calculate energy of the system. Once you calculate total energy of the system, you can calculate delta G. Once you calculate delta G, then you know the reaction is physical or not. Right? So basically, now how do you calculate energy of the electron? I'm not going to teach you quantum mechanics, but I will give you some idea. This equation looks very complicated. It is complicated, but it is also simple. I mean, I'll explain why it is simple. What these people did? So basically, we taught in chemistry, if you understand electron, like this photochemical reaction, if they understand electron, where the electron is going, which level, where it is getting excited, they can explain. Not only the photochemical people, even thermochemical people, whether they will be charged donation or not, right? Like if it takes electron from the oxygen, then this double bond will become weak and then it will interact and all. So basically electron donation and acceptance, right? That means the energy of the electron is very important. If electron energy is very high, then they will give electron easily. If the electron energy is very low, very difficult. It's like your ionization potential. You calculate ionization potential of the system, right? Now, how do you understand electron in your system? Think about this. Suppose this student, he is here, right? I don't know him. I know he works with Devan, right? But if I watch him for a month, just 1 month, I will see you what he is doing. Will I understand a bit or not? Right? For a year? Right? I know where, at some point I know where he goes at this time, what he does. Right? And that is true for electron also. If you watch electron over time, what it does actually, when it is close to the nucleus, what it does, when it is far from the nucleus, what it does, and when it is very reactive, very excited. So that's why this psi is the wave function. Wave function. Wave function is how it behaves over time. So that means if I know his function or one of your function, like your parents, they think that they know you better, but maybe they don't know. But at least they know a bit, right? Because they watch you, suppose, for 15, 20 years, right? Closely, right? So 15 to 18 years at least they understand, and then you leave and then they don't understand because they don't see you, right? After some time. So the point is, if you can watch the electron, how they behave over a long time, then you know the function of the electron. Once we know the function of the electron, that is the psi, H psi, that means we know its properties. Like if I watch you for a year, like I understand my students a bit. I don't watch them 24 hours in a day. I hardly watch them maybe 4 minutes in a day, right? But still I understand. And I don't understand you people because I even don't watch you guys for 4 minutes in a day. So what this guy said, that this is one electron wave function, means if the electron, what is the path, where it goes, how it behaves, then we can calculate the energy. So I'm not teaching quantum mechanics, but it is, this is what it is, right? So once we have the electron energy, then how many electrons is there, how many proton is there, how electron interacts, and how electron proton interact. So basically we can calculate the total energy. That's why computational chemistry is important. And then once you can calculate total energy of the system, because everything is about energy. Once you get the total energy of the system, then you can calculate any properties. It's like understanding the electron. So because most of the properties you see electronic properties, reactivity, it's the properties of electron. So if you understand, then you understand the properties of the system. So electronic structure is important. You all have studied molecular orbitals. That is actually electronic structure. Some inorganic chemistry, right? It's molecular orbitals of some simple system. So now going back, this reaction, basically we need to calculate energy of this plus this and then this, right? So once you calculate using quantum mechanics, computational tool, using this equation can do what? We calculate the total energy of the system, not only total energy of the system, total energy of the electrons. Once I know energy of the electrons, I can calculate the properties of whether it's active, not, everything. Every parameter we can calculate. Let's then talk about the catalyst. So this reaction, suppose delta G is, suppose this reaction delta G is minus 100 kilocalorie. Now if you use a catalyst, delta G will change or not? What is the definition of catalyst? Some of you know, right? Delta G will change? Are you sure?
Yes.
Delta G will change, right? That's why you use catalyst. Reaction energy will change? How many of you think it will change? All of you, anyone? Anyone don't agree the reaction energy will not change? No? So basically the concept of catalyst is not clear then. You all understand catalyst, right? What is catalyst? Lowers the activation energy, right? Does it ever say it lowers the reaction free energy? Why it doesn't say? Those you think the delta G will change? Have you ever studied that it will change the reaction free energy or reaction energy or energy? It always says activation energy. What does that mean? That means activation energy is important, delta G is not important. I said both are important, maybe activation energy is more important.
Molecules will need lesser energy
Molecules would need lesser energy to
to
collide and
give products.
any other perspective? So the answer is delta G remains same whether you use whatever catalyst. The reaction path change, I think you all have studied. Your activation barrier change. Because your reactant and product in presence of catalyst or in absence of catalyst, they are same. Your reactant is this two. Your product is this. Delta G is product minus reactant. What do you see the catalyst here? They are not there. They change the path. What I mean, they change the path. So basically, I can show you what exactly happened, and then we can discuss in detail, okay? And then we can talk about everything. So in this reaction, so basically what happens, you have a, suppose, I think metal-based catalyst, suppose platinum catalyst they use, right? So what happens, like you have a platinum, so you have a C2H4 plus O2, right, half O2. And then you use a platinum catalyst. So what will happen? Platinum will suppose bind both, right, C2H4, O2. And then they will react, whatever bond will form, some kind of transition state. Let's assume there will be transition state, right, C2H4. And then it will be platinum plus, right? Fine. This is the reaction, typically. So you see the energy in the reactant was here. And you can add the energy of the platinum also now. And here you want platinum back. So platinum energy will cancel. The energy of the catalyst will be cancelled because platinum is out. So basically it is the delta G is the difference between these two. I'll show you the reaction free energy. So basically what happened, this is a reaction free energy, typical reaction free energy profile. So this is my reaction, right? For any catalytic reaction, you know, this is the, suppose this is your product, this is your reactant. In this case, ethylene plus oxygen, product is epoxide, ethylene oxide, right? Now this is your delta G. Sorry, this is your delta G, this part is your delta G, and this is a barrier. Now when you use a catalyst, this part changes. Your product energy, reactant energy, so your barrier it lowers. This is your activation barrier. So delta G doesn't change because delta G is the difference between product and the reactant. Nothing to do with the catalyst. What catalyst does? It lowers the energy of the intermediate. Or you can say other way. You can say that in presence of the catalyst, energy of the reactant increases. Can you say that? So this is a reactant energy, this is a product energy. Now you can have multiple steps, right? As soon as there is a platinum, suppose this is platinum plus reactant, but energy is here. So earlier reactant energy was here, in presence of platinum reactant energy is here. Because once the reactant, the ethylene, it interacts, the total energy of the system suppose increases. So when it increases, automatically suppose this was the actual barrier, and this barrier also gets smaller, right? Because this is between this and this now. So basically the activation barrier that actually changes, not the right. Now there are two parts. One is enthalpy, one is entropy. If you see delta G equal to delta H minus T delta S. Now what is the role of enthalpy and entropy?
When entropy is increased for particular one system, then the spontaneity of reaction is exceeds to it means delta G is equal to minus.
Delta G equal to delta H minus T delta S, right?
If entropy increase, then spontaneity will be increased.
Entropy, yes, entropy increases, will increase the spontaneity of the system, right? Because not spontaneity of the system, unless delta G is negative. Even if we, so entropy positive is good because delta G equal to delta H minus T delta S, right? Okay, there is another scheme, so it's not a problem. So delta G equal to delta H minus T delta S, right? Now this value is what? Negative. Temperature is always positive, right? It could be 0 to whatever, right? So that means delta H positive is good. Delta H positive means whole term will be negative. I need delta G negative for a reaction to be spontaneous. So that means if entropy change in entropy is positive, that is good. Now change in entropy, any idea when there is positive change in entropy? Any idea? If phase changes, yes, phase changes there can be like phase changes, suppose it is solid to gas or liquid to gas. The randomness, this basically again going back same, like in molecules, they will have more kinetic energy. In solids they are tightly packed. I don't know how many of you understand the structure of solids, liquids and molecules, but maybe I can talk about that part also. Maybe we will talk. So basically randomness. So there are reactions, entropically driven reaction. Only entropy is important. But entropically driven reactions are very, very few. I mean, maybe phase changes, max. A reaction in like C2H4 plus O2 to epoxide cannot be entropy change reaction. Entropy change, like there is some change in the structure, like isomers. Some change in the structure. Because of that change, little change, you have some positive entropy. So it's an entropy driven reaction. Like ice melting, solid to liquid, that's an entropy driven reaction. Little change. Okay? So that can be entropy driven reaction. But enthalpy is the main important part. Enthalpy is the total energy of the system. Is that clear now? So enthalpy, so basically we don't worry about the enthalpy part, this part. Enthalpy is just your energy, right? Total heat content of the system. Now let me talk about the structure of some molecule. Like you have like if you have C2H4, what is the structure of C2H4? You all know, I guess. I don't think so, you all know, but let me see. How do you see the structure? It's very important for us. So this is the structure, whatever, right? Planar structure, you guys know, right? I forget about my drawing, but it's a planar structure, right? Not stereo, those plane and all, okay. But does one molecule? How many molecules are there? We talked. and Avogadro number of molecules are there. And how they are there? Huh? So suppose water. There is a steam, there is a liquid, there is this ice. What is the structure of water? And they're very important unless I know the structure for us. Because for experimentalist, you don't need to worry about the structure, but I have to model the structure. I have to get the correct structures. If I get my structure wrong, then I will not get the energy of the system. I will get wrong, right? So how many molecules are there? Avogadro number molecules are there, but how they are interacting? How many people are here? Maybe 20? The 20 people are there, but 20 people are sitting at the same place? These three here, C is there, they're there. How many molecules? Ethylene is there. Again, same concept. How they're there, how they're interacting. So if you have 10 to the 23 numbers of molecule, suppose I put 100, if I put 100 people, maybe 100 chairs, so you have no other options. But if I suppose put 10 people here, will they sit same way? Some people will sit there, some people will sit there, right? So that means the C2H4 can be interacting with another few C2H4. It's like a cluster. Now how many molecules are there? How many? C2H4. Total number suppose 10 to the power 23. Out of 10 to the power 23, how there? One molecule? No. One molecule will happen when it is an ideal gas. There is nothing called ideal gas. Right? So when it is gas, there may be very few molecules. When it is liquid, then they are packed. This is infinite structure, infinite structure. That's, I don't know if you have studied this periodic structure, solid structure, units and all. So basically when you have a gas, ideal gas, one molecule. But when you are doing any reaction in a liquid solution, then it is not one, you have 23 molecules, but they are basically interacting with each other. So if I try to understand one of you when you are alone, and when you are with one of your friends, the behavior will be same or different? You will not behave same, right? Then two friends are there, then you know what happens. Then three people, you know what happens. And when you are alone, okay. Same goes with molecules. That means I need to understand whether they are with one molecule, two molecule, few more molecules. Same goes with solvents, like you guys add solvents, right? A lot of solvents. Like when you add solvents, how many solvents really interact? Basically, what solvent you guys use mostly?
PCM, acetone.
Acetone, right? So acetone means one molecule acetone. Again, they will interact. Maybe suppose let's assume I have 4 C2H4. So this structure is also important because of their structure, their behavior will change. So let's say I have one molecule. Total I have 10 to the power 23 per molar solution, whatever, per molar solution. Now, one molecule, they do not exist. Ideal gas, they do not exist. So basically, let's say I have 10 molecules C2H4, whatever. And then you have acetone solvent. How many solvents is interacting with them? Maybe another 20. You don't know. No one knows how many. There are some reports, they can say how many solvents. So maybe at least, if it is suppose 10 molecules at the surface, at least you can say maybe 20 acetone molecule interacting. So once we know the structure, how they interacting, then only we can understand their properties. Like I said that like when you are with friends, you are different. When you are alone, you are different, right? When you are with a group of people, different. Same goes with molecules. That's why structure is important. So that's why solid, liquid, gas, they behave different. Their properties are different. This is the reason. The same molecule, same element, same structure, more or less, but their properties are different because they are more clusters, more packed, right? And that's why their melting point and boiling point and everything they do change. So now this is the part I talked mostly about energy, delta G, and now let me talk about, I talked also a bit about why computational chemistry, what computational chemistry can do. They can using this or in the equation we can calculate energy, and we need energy. Unless we understand the energy, we will not be able to calculate the delta G. If we do not able to calculate delta G, then we will not know whether the reaction will happen or not. But there is like, but then how we help, right? So basically you have done a reaction, any reaction like this ethylene epoxide, but then you want to try some new reaction. You have some idea, right? That this if I mix this with this, whether this reaction will happen or not. Now, as a computational chemist, like what they do exactly? So they need to understand the structure first, because we have to understand the structure first. Unless we get the structure correct, we cannot calculate the energy of the system correctly. If we don't calculate the energy of the system correctly, we will not be able to tell exactly the reaction will happen or not. Now, you know this is the structure of the ethylene, right? There is one part I said that how many molecules are there, how many molecules, how they form cluster. And one is what is the structures. What I meant, let me go back again. So role of solvent, role of temperature, all these more or less clear, right? What exactly they do. Now you know this is your structure. Sorry. We will do here. So this is you know as a ethylene structure, right? Now if I say no, this is not the structure, this is the structure. I'm sure you all will not agree to me, right? But how do you know that is the structure? And how many combinations you can have? I mean, why you know this is not the structure? Balance. So if you know the valency, can you tell me all the structure? Does valency explain everything? I can give you plenty of structures that valency doesn't satisfy. Do you know this structure exists? Forget about valency. Do you know this structure exists? Is there valency fulfilled? C2, yes C2. There are a lot of papers, just you Google it. I have also a paper in C2, first paper. Does it exist? Yes, it exists. So does valency satisfy there? How many of you studied boron clusters? Does valency fulfill there? Boron clusters, closer borons, or widow borons, right? Now, how do you know that is the structure of the ethylene? Because of the valency or because you studied, read in the book? Which is true? Because that is the structure you have been taught, right? Now, and this, the possibility can be used. How many possibilities are we talking? Any idea? So to understand a reaction, see, this is for a known reaction is simple. For an unknown reaction, we need to understand the structure. And because even many times you even don't know what is the structure. You are trying something new, you don't know what is the structure. Maybe you know the structure of the reactant, but you don't know what is in between you got, right? And then they do lot of characterization, NMR, mass, IR, this, that, and then also if it is a molecular level structure, I mean like cluster level structure, then also like hydrogen, position of the hydrogen, they're very difficult, right? Now this particular structure, if I say this particular, I mean with C2H4, 6 atom, this one, if I say there can be 1,000 structures, would you believe me? 1,000 structures. You know about one structures. How many of you believe me that there can be 1,000 structures? I'm happy you don't believe me. That's nice. That means you are learning something new. Is it possible? That's good. Let me start now. Okay. So for an unknown system, like for the known system you are studying in textbook, you have the NMR, you have the structure, you have the mass. For an unknown system, you ask me, sir, I mean, let's do it, right? That means I have to guess the structure. And when I have to guess a new structure, totally new structures, then I can even try 1,000 possible structures, minimum. We have done it for some systems. Not for this kind of systems. I will tell you a system like platinum 7. This is a cluster. 7 platinum atoms. Now can all of you tell me what would be the structure? Even when you all know. Can you tell me what is the structure of platinum 7? Now how would I know what is the structure of platinum 7? Only 7 of them. I'm not talking. How many atoms in a structure? Any area? How many atoms in a structure? Any structure? Not ethylene. Suppose a how many of you work on nanoparticle in PhD people, and how many of you heard about nanoparticle? You do nanoparticle? What nanoparticle?
Yeah, copper nanoparticle.
Copper nanoparticle, right? Yes. How many atoms are there? Yes.
Number.
Yeah, Adam, we'll talk about the structure later. Let me see nanoparticle. How many of you are working? Nanoparticle. How many of you have heard the term nanoparticle? Nowadays, I don't think everyone knows, right? Nanoparticle. How many atoms are there? What is the nanoparticle? Copper. Copper. Copper nanoparticle. What is the size?
So within 100 nanometers.
Any idea how many atoms are there? Now Avogadro concept will not work for those who are worried about Avogadro number. So copper, C talks about it, maybe 100, C said just 100 to say 100. 100 is like not a nanometer, it's a nanometer, fine. Bigger size nanometer, right? How many atoms? Anyone have idea? No one have any idea. Forget about the structure. You don't have an idea how many atoms are there. I said for platinum 7, that's not even 1 nanometer. Platinum 7 may not be even 1 nanometer, not even 1 nanometer. It's maybe point few. It's a sub-nano cluster. They call sub-nano because even less than 1 nano. 1 nanometer is around 100 atoms. Let me tell you how many atoms. Can you tell me how I calculate how many atoms? Typically, I will tell you what is the number of atoms is there in the 100. Those who don't know and want interested do know. What is the distance, copper distance? What is the carbon distance? What is the carbon single bond distance? Anybody organic chemist? So all are organic chemist. I am a physical chemist. Carbon distance? 1.54. Perfect. That's a single bond distance he is talking. Let's forget about copper. Let's carbon. It's easy because, or we can do copper. So any idea how 100 nanometer means how many angstrom? One nanometer is 10 angstrom. That means 100 into 10 angstrom. Right? That is perfect, right? Now let's carbon bond distance 1.54. Let's say copper bond distance 2 angstrom. Metal, right? Let's assume 2. This is 2 angstrom. I have to cover 1000 angstrom. So how many I need to add? 500 at least. Then it will be 1000 angstrom. If each bond is 2 angstrom. If it is 2.5, it will be little less, right? So how many atoms? 500 for one dimension, 500 for another dimension, 500 for third dimension. So 500 into 500 into 500. How many atoms? Typically, 500 for this dimension, 500 for y direction. It's a 3 dimension, z direction. So 500 into 500 into 500. So this is 25 into 10 to the power 6 atoms in your 100 nanometer copper body. (125 into 10 to the power 6). Can you tell me the structure? Atomic structure. You don't see this term and all. Atom, how they are distributed. Do you understand the problem? I mean, how complex is this, right? Now, if I ask how many possible combinations with this many atoms, I mean, it's infinite. Even nobody can tell actually, right? But you need to understand the structure. If you give me a 100 nanometer nanoparticle, I may not get the exact structure, but I can get very close to the structure. Because I now know typically how many atoms are there. And the structure generally what happens, like, because it's a big size nanostructure, copper metal, it has a structural pattern. So it will more or less follow copper bulk, copper metal, the copper where you see the structure. That structure more or less will follow only the surface. At the surface, it's like a football, right? These many atoms. At the surface, they will be different. The atoms orientation will be different. Now going back, this is a big cluster. So how many atoms in a 1 nanometer? If it is a copper, only 10 angstrom, right? So it is a one, suppose nanorod. If you talk about a nanorod, then basically 5 atoms in only 1 dimension, 1 nanometer. So each copper 2. So basically 1 angstrom is 10 nanometer. So 5 in 1. If it is a 3 dimensional, then it will be 5 into 5 into 5. So 125 atom for 1 nanometer. Typically 1 nanometer is close to 100 atoms. And then it will change exponentially. It's not that you multiply it by 100, so you will get 1250 atoms. No, 500 atoms. No, you will get the number I showed 125 into 10 to the power 6. So basically 125 million. 10 to the power 6 is 1 million, right? 125 million atom you got. And if you understand, if you have to calculate that properties and all, so they are huge. So this is how. So for a new system, like I said, for any organic chemistry. So what computational chemistry can do for an unknown system? Known system anyway, very easy, right? I mean, at least we know the structure. For unknown system, I have to then guess the structure. And it's not very simple. You have to have, so you have to have all possible ways. How possible ways, I'll maybe give you an example. How possible, it's like, suppose you have two atoms. If you have two atoms, this is the structure. Whatever, maximum your bond length will be different, right? This bond length will be either maybe 1.2 angstrom or whatever. So the possibilities are not much. But if you have the three atom, then this third atom can be here, 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 can be here. You see the possibilities. How many possibilities? The fourth, then you bring fourth atom. So basically you're like 7 atom I said, now you believe the possibilities are huge, right? Now the interesting part. Now how many of you know this ethane structure? Ethane is simple, right? I'll connect them. Ethane is simple. Or maybe let's take a cyclohexane, the chair and board, right? One is a chair and one is a board. So in cyclohexane we know that these are the two structures exist. And one of them is very stable, the other one is not, right? Now when you do a reaction, suppose taking cyclohexane, then you assume the most stable structure that is present in the reaction. Tell me, is that always the case? Then I can go back to ethylene. When you have ethylene in the structure, in your reaction condition, ethylene is still ethylene or different? What I'm saying is, suppose this is a cyclohexane and chair and board structures. Now you do a reaction. These are the two possibilities, right? And suppose their energy difference, I don't know what is the energy difference, maybe not much, maybe suppose 5 kilocalorie. That means if the energy difference is less between these two structures, then they can interconvert. I mean, chair can become board, board can become chair because the energy difference is less. So when you are doing reaction thinking your chair structure is there, it may happen that basically in the process it became board and then you got the reaction, you got the product, right? You do NMR and all, you know it. Now this energy difference is 5 kilocalorie, but when you do in the nanocrystals, the energy difference is very, very low. So most stable structure, you have a ground state structure, we say ground state structure, GS. So that is one. And then there is called excited state structure or metastable state structure. So basically whenever you are doing a reaction, even forget about simple reaction, ethylene in the reaction condition may not be ethylene. It may go to one of the ground excited state structure. When it goes to the excited state structure, then the possibilities, whatever you are doing, the possibilities, the reaction. Now again depend, like for ethylene, what is the difference, energy difference between excited state and ground state? If the difference is huge, then no, it will not go to the excited state structure. But if the difference is less, then it will easily go to the excited state structure and then you will get totally a different product. So for an unknown system, they are more challenging because we do not know the structure, and even if we suppose find out the structure, what is the next most stable structure? If the next most stable structure is the energy difference is very less, that means both of them reacting at the same time. So the product you get, you are not sure whether you got from the ground state structure or most stable structure. So these are called metastable structure and excited state structure. Now this is the structural part. Now maybe I'll cover about this photochemistry something. What exactly happened? So this is about, I talk about thermal catalysis. But what happens in photocatalysis? Do you have a break or what? We have a break, or we say continuous 2 hours? Continuous 2 hours, okay. So now let's talk about photocatalysis. So any questions you have for the thermocatalysis one? No question. So what about photocatalysis? What exactly happens? What exactly you do and what happens? Delta G is important there? Delta G is important. Delta G is still there, right? Yes. Then what is not important there? What is the difference between thermocatalysis and photocatalysis? Organic synthesis, nowadays people are using even electrolysis, right? Electrocatalysis, right? Even for organic synthesis, right? And what are the differences between these three? So catalysis can be of different types, right? So what is the mechanism?
Thermocatalysis direct heat energy is applied.
Yes.
Photocatalysis, and when photocatalyst is used, this increases the activation energy of the electrons.
Okay. Anyone, any idea? So what is the difference between thermocatalysis, photocatalysis and electrocatalysis? Electromagnetic, this is light, okay, light is electromagnetic, okay, so basically you sign with light we call electromagnetic radiation because it has both electric and magnetic properties, that's why we call electromagnetic radiation. So different range of light you sign with, and then
Mostly visible light.
so you do because visible light photocatalysis, right? And then what exactly?
Mostly catalyst absorbs the excited state.
It will go to the excited state and then it will react.
Then it transfers the energy to the molecule.
Yes. So let me talk about the differences. So simple catalysis, which you all know, that is now, because these fields are growing, this photocatalysis and electrocatalysis is growing, then we have to name it differently, right? One is thermocatalysis, one is photocatalysis, one is electrocatalysis. When we studied, we mostly talked catalysis means thermocatalysis, right? So in thermocatalysis, the same reaction, ethylene plus O2. Ethylene plus O2, this epoxide, right? So energy of these systems are important, right? So basically you apply temperature or pressure, total energy of the system changes and they kind of react. In a photocatalysis, electronic structure. Now the electronic structure is important. I don't know whether you know about electronic structures. Maybe ethylene has 2 pi bond here. So this is your HOMO, this is your LUMO. How many pi bond in ethylene? Maybe 1 pi bond, right? So yeah. So you have 1 pi, not 2 pi, right? So this is your ground state electronic structure. It's like molecular orbital. So basically what you happen, you give light and light will interact with this and it will excite and the electron will go here. So basically this electron will go from here to here. So this is an excited state. Now this electron can go in many possible states, but this is the excited state, and this excited state means now it is reactive. It has a lot of energy, and then it will react with the oxygen molecule, and then you will get, suppose, I don't know, it's a photocatalysis reaction. This reaction also works as a photocatalysis. I don't know whether this reaction, so there are some reactions they work for, same reaction can be synthesized using different ways. So in this case, but you tell me why light interacts with electron. Any idea? And which light and why? Any idea why light interacts?
Light interacts with the
Photocatalyst. So wavelength length of the light matches with the band gap of the photocatalyst, and that's why it interacts, and that is fine. But why? What is light?
Sir, actually, electron has also some wave property. So, we consider the property of the
So it is the wave properties or the particle properties? What is important?
interacting with the light is wave property of the electron.
Then why it will move?
Sorry.
Why it will move? Why it will go to the higher energy? How many of you understand particle? Electron is a particle? Electron particle or wave? Dual nature. What about light? Light also dual? So light is electron?
Photon particles.
Light is
Photon particles.
photon. So which property is here the important? So basically they are particle and wave both. Actually any small whether electron or photon or phonon or whatever, they are all both particle or sound.
Yes, sir.
Sound wave or particle, right? Or both, they have both nature. Now basically it interacts with the basically let's say homo-lumo gap. So if your homo-lumo gap of the photocatalyst matches with the wavelength of the light, then it excites. When it excites, it goes to the excited states, and when it goes to the excited state, it is very excited, so it interacts with the substrate. Now it can happen that it can interact both at the excited state or maybe once they come back and to the ground state and interact. So that is the photocatalysis, right? Now different wavelength they use, and then I can talk about all these in details, how they actually work. So there are one is your electronic energy. I talked about this, right? So molecule has different type of energy. One is kinetic energy, one is electronic energy, and then there is called potential energy. Potential energy, actually this part is potential energy. There is other kind of energy like different energy like dispersion energy, electrostatic energy. There are a lot of types of energy, but this one is called potential energy, one is called kinetic energy. Now this part is important, what I talked for when you apply temperature and pressure, the kinetics of the molecule linkages, they collide, and but this part is very important when you talk about photocatalysis or even for electrocatalysis. So basically the electronic energy, the potential energy, they are very important. Now I'll slowly explain what I am trying to say here. So suppose this is a called potential energy diagram. Sorry. Like I talked about, you all know about isomers, or forget about isomers. Let's talk about graphite and diamond. Let's go back there. This is graphite and this is diamond, right? Delta G I said will be close to negative. Let's assume that this difference delta G is close to 0, right? Now this is the potential energy. So basically same element, carbon, and they can exist in this state and this state. One is more stable than the other. So does it mean that the structure which is more stable only exists? Like in this room, I'm sure someone is very stronger, right? Does that mean that person only exists here? That means others also, right? We must be weaker a bit, right? But we still exist, right? Somebody is very strong, that goes for molecules also. That's why you see a lot of isomers. That doesn't mean one is energetically less stable, doesn't mean it doesn't have any rights to exist. That also do exist, and they have different properties, right? Let's say graphite is the most stable, the pencil. Doesn't mean diamond is not very stable. Diamond is much more stable, right? It's very hard, right? But it is not thermodynamically most stable structure. But once you get that structure, so that is more. So this is what I talked about energy. The stability can be of different type. This is a total energy, mechanical stability. So a molecule is like we all know, right? Somebody is physically strong, right? Same goes for molecule. They are energetically stable. Then there is a called vibrational energy, like electronic energy, and then there is called thermal energy. Thermal energy means whether they are thermally stable or not. So basically you hit the molecule, whether the molecule will break or not, or will change into a different structure or not. So suppose up to 100 degree, 200 degree, 300 degree, the molecule doesn't change to a new structure. That means that molecule is thermally stable. One I talk energetically stable, the total energy. One is thermally stable. Then there is a called dynamically stable. The vibration, molecule vibrate or not. So if some molecules when they basically you know that atoms they do vibrate, right? So the vibration will be due to the vibration whether they dynamically stable or not. So then there is a called mechanical stability. So basically you stretch the molecule, the elasticity. You stretch the molecule, it will go back. So they are like rubbers, right? They are mechanically very elastic. They will go back. They are very stable, but they are not hard. So that is called mechanically stable, right? So these are the different properties of the molecule, different stability. So you cannot say graphite is more okay. You can say, okay, graphite is more stable based on the maybe total energy, but not really graphite, graphite is the most hard, graphite is very soft, right? So that is, so same goes for molecules, electronic properties. So basically you know a ground state structure, but then some molecules, the moment you shine light, so they react. They go to a excited state. So that is the another electronic state. The first one I talked about the molecule, the atoms. I didn't talk about the electron. In the first case I talked about only atom. Total energy of the system, vibration, mechanical, all atomic stability. Now there are electrons in the atoms. These electrons, how they respond, right? That's why these two fields emerge. One is electrocatalysis and one is your photocatalysis. So now when you shine light, molecule, the structure will not change. There is hardly a change in the structures, but it will go to the excited state. So the molecule, atom bond states are more or less same. I mean, they do not change because this electronic transitions, they happen very, very fast. They go to the excited state, they come back. Before even the atoms, they realize, okay, my electron has gone. It's like sometimes we see that the children, right? Sometimes they are out, right? Somewhere they gone and then they come back. So basically, electron goes to the excited state and come back. But in that time, if it reacts, if it gets something, it will react before it come back. So you excite the electron, it gone to the excited state, and then it found something to react, it got reacted, you got the product. So electron didn't, so before it came back, right? So that is the electronic properties. You just need to understand the differences between atomic energy, atomic structures and electronic structures. So atomic structures is the talk I talked, mechanical properties like rock, they are very solid, they are hard, and then elasticity and all. Now so in this case you shine light, and if the volume of the light matches with the excited state of the molecule, it will get excited and it will come back within in the maybe 10 to second, 10 to the minus, I mean very fast, 10 to the minus 15 level, right? But in that moment, if it gets something to react, it will react and it will give a product. Now there is another field that is called electrocatalysis. I don't think you guys do. What happens there? It's like the mobile cell, the battery you are using. You just using, so it's like electrochemical device. So suppose you are using the lithium batteries, right? So what do you do? So this lithium, it's the same like graphite. Like this lithium is there inside the graphite. So you have a lot of, so what happens? You have one like electrode here, lithium, sorry. You have suppose one electrode here, you have only lithium, right? And there is another electrode that is called graphite. This is a graphite layer. So you charge your battery. What happens when you charging this lithium? What they go here, they stay here. So some of the lithium, suppose you have 10 to the power 10 lithium here, actually much more, right? Suppose here 10 to the power, suppose 5 lithium gone. Your battery is charged. And how do you charge? You plug it, right? So this is a exothermic reaction or endothermic reaction? So if one is endothermic, the reverse has to be exothermic, right? Otherwise it will not happen spontaneously, right? So when you are charging means you are giving energy, and then only lithium is going. So is it endothermic or exothermic? It is endothermic. Otherwise your battery will burst actually. You were during charging, and that's what happened. Why it burst? Because this lithium doesn't want to go. And when you use the battery, or a very bad quality battery, this is not like enough, I will not go. So it will heat it up, right? And then once it is there, then when you are using this lithium actually going back to your general electrode cap. So this is an electrochemical process where an electron are actually going out of the circuit. Okay. So this is electrochemical tricks. Basically, what we are doing, we are taking out the electron of the systems. Whatever, this gone. This pencil is okay. Yes. So that is so basically in one case the difference is, in one case you are shining light you are using for a reaction, and we are using the excited state of the molecule. In another case we are using the we are not actually exciting, we are taking out the electron, like it is the energy of the electron is important. Now let me I don't know what's happened now, it's taking so much time. Okay, maybe news. Anyway. Suppose these are of your, suppose this is your HOMO, anything, any system, this is a HOMO, right? And this is your energy scale. Right? This is lower the energy, this is -10, this is -9, this is -8. So basically this electron is more stable, this is -10, negative is better, right? Now if I want to take out this electron, how much energy I need? I have the scale, you see the scale, -8, whatever, if it is suppose in electron volt. So that means you need to give this much energy to take out the electron, right? Now you are doing a reaction, whatever, even a photocatalysis or electrocatalysis. Suppose I want to do a reduction of simple molecule, right? Suppose CO2 reduction is very important, right? So that means CO2 has to take an electron. So CO2, that means if it takes one electron, it will be CO2 minus, right? Now, so basically suppose this is your electrocatalysis, this is the electrode. Suppose this is a copper electrode. And this is my energy scale. Now I will draw the energy scale of CO2. This simply it's molecular orbital. We basically don't know how to draw the molecular orbital, even I don't know. But what we can do, we can use computational tools. We can calculate the energy of these states. What is HOMO, what is LUMO. Now I calculate, suppose, energy state of, it's not working like before, I don't know why. Whatever the reason, forget it. Okay. Okay, then it will work. So let's suppose this is a LUMO, right? And this is the HOMO of suppose CO2, whatever. Now you tell me whether this electron will go from here to here or not. Where it will go? if the LUMO is here, it will not go. Why? For any reaction, there is two types of reaction. One is oxidation reaction, one is reduction reaction. So for reduction reaction, your electron has to go to the LUMO. For oxidation reaction, the HOMO electron will go, right? Now, how do you pick your catalyst? Which catalyst is important for a CO2 reduction? So basically, I need to know the energy level of this CO2 molecule, and then there is a called reduction potential. You all have studied, right? Reduction potential. So that means CO2, how many electrons it needs to be fully reduced? Suppose CO2 to CH4, how many electrons you need? There are a lot of products for CO2 reduction, CO, HCO, whatever, HCOH, whatever. So suppose you need up to 8 electrons, right? Now each electron, so for one electron, there is a reduction potential values. So for one electron reduction, suppose the value is around 0.05. For second electron, suppose 0.10. For third electron, suppose 0.20. That means this particular energy gives an idea that where my energy should be. So basically this state, the state of the catalyst should be higher in energy than the LUMO state of the CO2. If it is lower in energy, then there will be a transfer. Now for any reduction to happen, we need to know the electronic states. Or we can say, at least we need to know the ionization potential. If you know the ionization potential of the electrode, how much energy you need to give to take out an electron, and then if it matches with your reduction potential of the molecule, then you can say that this could be a good catalyst. And again, same thing, delta G equal to delta H minus T delta S. Basically, this equation has to follow, your delta G has to be negative, and but in this case, there are two criteria. One, kinetic criteria is not important. In the beginning I talked, for a photocatalysis and electrocatalysis kinetic, its delta G is very important. And delta G comes from your energy state of the molecule. So for any electroorganic synthesis, suppose you are doing any synthesis, suppose ethylene oxide, that means how much energy I need to give, or how much energy suppose the electron has to go from oxygen to ethylene. That means the LUMO energy of ethylene is important, because the electron will come to the LUMO of ethylene. If you know the LUMO energy, and that is nothing, electron affinity. LUMO energy is actually your electron affinity. HOMO energy is actually your ionization potential. So once you know the electron affinity of the molecule, then if you know that what is the phosphorus molecule, where from the electron will come, what is the ionization potential of that molecule. If they are very close, then there is a chance that the electron will transfer from this, and that you can exactly see from the electronic states of this molecule. So ethylene, the LUMO is a pi orbital. They will take the electron when the molecule has the ionization potential close to the electron affinity of this ethylene. Okay, so this is how electrocatalysis work, and then the photocatalysis I also talked. And let me know if you have any other questions. I am not talking about quantum mechanics. I am sure this itself becomes very difficult. Quantum mechanics will be more and more complex. Let me know. Any questions? Any question? Maybe questions related to your research. Those PhD students. If you want to clear some of your doubts, let me know. Yeah.
Actually, nowadays the organic sciences many papers that we have seen that they have some computational studies along with the organic part. So, as an organic chemist, we don't have the exposure to study computational chemistry in our graduation and masters. Where can I learn it from the scratch, computational chemistry?
So you want to do both, or synthesis as well as
Just the basic parts.
basic. See, you can do calculation. There are a lot of people they do a lot of calculations, right? But I will not recommend that. I will say either. I mean, I know there are groups they do both theory as well as experiments. Fine if they have a dedicated students who are really doing theory, but training is very important. What I mean, it doesn't happen overnight, right? So this theory behind this, and you tend to do a lot of mistakes. So unless you have someone who can cross-check your results and whether you are doing correct, I would not recommend both. I mean, there are groups I know do. I'm not a big fan of them. I mean, I'm sure they make. I don't know. I mean, I doubt. So that's my recommendation. There are people they think differently. They do both, and I have been in those committees, and I have realized they don't know anything. So I would not recommend. If you doing PhD in maybe in outside India, and there are big groups, but if you look closely, what they do, they hire experts. So suppose they take a student from my group as a postdoc who has done totally theoretical calculations, right? And then they hire the postdoc and then they keep on training. So the training is done maybe under one of the theoreticians. Any other question? No other questions? Oliver, you have any questions?
No, I want to see what you're doing. That's all.
No other questions? So many things we discussed, I guess. Any other? Okay, then we finish here.
I was just walking over the campus and I thought I'd stop by and see what
Yeah.
you're doing, but I missed everything apparently.
So it's quite hot nowadays.
It is relatively hot, yeah. 35 degrees.
So you're feeling the heat?
Yeah, sure. But it's not too bad.